After more than 2 years of travel, on December 3, 2018, the OSIRIS-REx probe finally reached its target, the asteroid Bennu.
Asteroid Bennu is a carbonaceous type asteroid, so that means it's predominantly made of carbon, much like we are here on Earth and what primarily Earth is made up of.
The culmination of this NASA mission's adventure will occur when the spacecraft sampling arm touches the surface of Bennu, collects some asteroidal material, and brings that sample back to Earth. This tiny sample will allow us to answer big questions, like where we come from and what is our destiny. Bennu hides secrets about the history of the Sun and planets, as well as the origin of life, since it, like all asteroids, is the leftover debris from the solar system's formation process.
Asteroid Bennu is an interesting asteroid to study for a number of reasons. It's the first carbonaceous type asteroid that we've gone out to collect the sample from. And carbon type asteroids are the type of asteroids that could have brought life to Earth in its early days of formation.
Bennu is just one of the hundreds of thousands of asteroids that float in the space in our solar system. These tiny rocky worlds are irregularly shaped, though a few are nearly spherical, and they are often pitted or cratered.
So most asteroids are located in a belt between Mars and Jupiter that we call the asteroid belt.
However, there are more asteroids in other locations. The so-called Trojans are asteroids that share an orbit with a larger planet, but do not collide with it.
Trojans are just objects that happen to be at what we call a Lagrange point of a planet. The Lagrange point is 60 degrees before or after. And the way to think about it is that if you take a planet and the sun, the gravitational force of an object at exactly 60 degrees between those two objects, plus the centrifugal force of rotation, all cancel out. So if you put something at that 60-degree point, it'll stay there forever. And so these Trojans, therefore, are leftovers of the formation of the planets. And that's what makes them so interesting, is that they're an ancient population that shared an orbit with Jupiter.
The main population of Trojan asteroids are the Jupiter Trojans, which is thought to have as many asteroids as those in the asteroid belt. There are also Mars and Neptune Trojans. However, they are not as numerous as the Jupiter ones. The other major population of asteroids is the near-Earth asteroids.
There's also near-Earth asteroids, and these are asteroids that cross the orbit of Earth. So they're ones that could potentially hit Earth.
The near-Earth asteroid population is about 1,000 times less populous than the asteroid belt. The main asteroid belt has about 1 million objects larger than about 1 kilometer. And the near-Earth object population has about 1,000 objects larger than 1 kilometer.
However, not all asteroids that float around our solar system belong to one of these populations, near-Earth asteroids or Trojans, or are trapped in the main asteroid belt. There are rare exceptions. On October 18, 2017, an unexpected discovery shocked the international scientific community. Astronomers discovered that a very weird asteroid passed by the Earth.
This asteroid seems to be at least 3 times as long as it is wide. It is possibly as much as maybe 8, 9, or 10 times as long as it is wide. This is something we have yet to see in our solar system, and how it gets produced is something we're not sure how to do this at this point.
The object was initially thought to come from the Oort cloud, a region far outside the solar system, which can have extreme orbits that take them careening through the inner solar system at speeds exceeding 37 miles per second. This strange celestial body was so significant because it moved at the astounding speed of 54 miles a second, too high to have come from our solar system. The conclusion was clear. It had to have originated from another solar system, making it the first ever discovery of an interstellar object. They named it Oumuamua. which means something like first distant messenger in Hawaiian.
Oumuamua is the first interstellar asteroid we've ever seen. So this is an asteroid that came from another solar system. And it came and it passed through our solar system and is on its way out of our solar system. And that's really amazing because we live at a unique time when our telescopes have gotten better and we're scanning the skies regularly and we're able to detect this first interstellar asteroid. It is likely that other objects have passed through our solar system and we just never were aware of it.
Perhaps it is a messenger from another star system, but what can it really tell us about where it came from? Since it was moving so quickly, the time available to study it was extremely short. As a result, soon after its discovery on October 24th, a wild race began between astronomers from all around the globe to obtain telescope data and unveil its secrets. We were able to analyze Oumuamua's chemical composition using photometric colors and spectra that revealed that it has a reddish color and might have come from the inner part of its original star system. However, the great mystery surrounding this interstellar object was its extraordinary speed of 54 miles per second, much higher than any other object from our solar system.
That object had anomalously large non-gravitational forces. So that was a little unusual. With comets, when you see non-gravitational forces, you tend to see dust produced because the gas is escaping and it lifts the dust off the surface. The interesting thing about this object is we didn't see any dust. So the question is, how can you get gas escaping and not produce dust? And that's telling us something that this object is unusual, at least compared to objects that are made in our solar system. And that's sort of a mystery.
Although we don't know Oumuamua's exact composition yet, we know the composition of asteroids that have been observed and studied for decades. Most asteroids fall into the following three categories: C-type, S-type, and M-type. C-type, or carbonaceous asteroids, also known as chondrite asteroids, are the most common. Their composition is believed to be similar to that of the Sun, although they lack hydrogen, helium, and other volatile compounds. They are dark in appearance, and they are among the most ancient objects in the solar system. S-types, or stony asteroids, are made up of silicate materials and nickel iron. They account for approximately 17% of all asteroids, and they are the second most common.
One is one we call S-type. These are often ones that were referred to as more stony type objects, and we think are very similar to a type of meteorite that's very common that lands on the Earth called ordinary chondrites.
M-type asteroids are metallic and much brighter than C-type asteroids. They are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed with different amounts of stone.
M-type asteroids are very unusual. Some of them may actually be metal. They may actually be produced in the interiors of asteroids. The core materials managed to escape the asteroid, probably in some gigantic collision. Other M-types, though, may be different compositions altogether, and there's still a great uncertainty about exactly what all of the M-type asteroids are.
If we want to study the composition of an asteroid, one of the best ways to do so is to analyze meteorites at an automated mineralogy lab, since many of them come from asteroids. The team at the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can examine the compounds of any meteorite sample with extreme precision.
All meteorites are fragments of rocky or metallic matter that's been transported from objects out in the solar system, and they've landed on the Earth's surface. And we can collect them and study them in the laboratory and work out their chemical composition, which minerals they contain, and therefore we can extrapolate the resource potential of particular bodies that exist elsewhere in the solar system.
Our automated mineralogy system is SEM-based, so we're using a scanning electron microscope to basically scan our sample. We have to prepare the sample. It is really important that our samples have a perfectly flat surface. So we have to polish our samples down to 1 micron. So the surface is perfectly even, so when we have the beam interact with the sample, we don't have other interaction features that will change the result of our interaction. We have our electron beam interact with the sample, and then we investigate basically the interaction product we get from the beam interacting with the sample. The result from this interaction we compare with the lookup table, where we have definitions for all minerals and phases that are of interest to us. And then our software program, the automated mineralogy software, will produce a false color map based on the definitions written and based on how it compares the analytical data with our lookup table.
Therefore, we can determine if the sample has more or less iron, nickel, platinum, or more or less of any other mineral. All asteroids, no matter their composition, are rocky remnants left over from the early formation of our solar system about 4.6 billion years ago. So they offer us clues to unveil the most hidden secrets of our most remote past. We've been exploring and studying asteroids for decades to understand what happened before us, before life on Earth, and even before Earth itself. Asteroids, considered floating fossils, can help us trace the solar system's evolution from a primordial disk of dust and grains. Asteroids can help us understand how the planets were formed and the origin of life on Earth, since there are theories that claim that the massive impact of asteroids was mainly responsible for delivering elements of life to primitive Earth. Asteroids are not just remnants of the remote past. They are also real hazards to Earth. Some pass close by Earth and could hit our planet one day, as occurred in the past when one ended the reign of the dinosaurs.
There was a 10-kilometer asteroid 60 million years ago that hit Earth. That's one of the current stories about the dinosaur ending event. Presumably we could have another asteroid impact like that at some point in time in the future, although right now it's not showing up as likely. We haven't found it yet.
A few years ago we saw an object the size of a large office building impact over Chelyabinsk, Russia. Very much smaller scale event, but still, in some ways, devastating for that particular city.
Scientists continuously monitor Earth-crossing asteroids, whose paths intersect Earth's orbit, and near-Earth asteroids that approach Earth's orbital distance to within about 28 million miles and may pose an impact danger.
The question is what to do about this. So right now, NASA has several ground-based surveys that use telescopes to scan the sky and look for threatening asteroids. They're trying to find all the asteroids that might present a threat to the Earth in the future. So far, we've had some success with this, where we think we've found all of the 1-kilometer asteroids and larger bodies that could hit the Earth. But as we go to smaller worlds, we go to, let's say, worlds that are half a kilometer or 100 meters or so, these objects are still threatening. We're still working to find some of these bodies.
Bennu, the target of the OSIRIS-REx mission, is one of the most potentially hazardous asteroids to Earth that is currently known, even though its odds of colliding with Earth are still relatively small.
NASA hasn't been able to control or change the trajectory of any asteroids yet. We are really at the beginning of understanding the types of asteroids that could impact Earth and how we might redirect them, which is one of the goals of the OSIRIS-REx mission, is to understand how the asteroid Bennu actually orbits and what we might do in the future to redirect it.
In fact, there is a NASA mission, the DART mission, that will test a technique for defending the planet from a future hypothetical asteroid impact, the main goal of which is to attempt to change the trajectory of an asteroid. Currently, there is no coordinated international plan to act in the event a potential hazardous asteroid is detected. Nevertheless, there are several non-governmental organizations that are focused on this issue. One of the most active is the B612 Foundation, which works toward protecting the Earth from asteroid impacts and informing and forwarding worldwide decision-making on planetary defense issues.
There are a number of groups worldwide that are concerned with asteroid detection and defense, and one of them is the B612 Foundation.
The B612 Foundation works to make interpretation of asteroid data open and accessible, and serves as an informed source for an international community of policymakers and scientists who can best help to achieve these goals. We haven't had any of these extinction-level events in recent history, but there might be one in the future if we don't do something about it. Some of Earth's largest craters, which are millions of years old, are large enough to hold a big city or even a small country. One of the most stunning craters that was recently discovered was in a remote area of northwest Greenland, buried under 0.6 miles of ice. It's 1,000 feet deep and 19 miles in diameter, which is bigger than Paris. That crater formed less than 3 million years ago, when a meteorite more than half a mile wide smashed into that area. The devastation that an impact like that could cause today would be catastrophic. Over the last decade, governments have started to gain awareness of this threat and have begun to make progress on the planetary defense front. With the ground-based U.S. National Science Foundation's Large Synoptic Survey Telescope, the LSST, 5 years from entering service, and with the selection of the Space Telescope NEOCAM as a finalist in the NASA Discovery Mission Program, scientists will be able to track 90% of near-Earth asteroids larger than 460 feet in about a decade.
We have to do something, or one day we will not be around anymore to ponder the asteroid problem. The asteroid problem will have done away with us.
Asteroids are among the oldest celestial bodies in the solar system. As floating fossils that witnessed Earth's primordial stages, they convey key information about the origin of life, as they are believed to have delivered the elements of life to Earth during its early stages.
Asteroids are fascinating celestial bodies that are somehow misunderstood. The asteroids hold the answers to many of the secrets that can help us to understand our own planet.
In addition to asteroids, comets and other small bodies offer clues that can help us understand Earth. Comets are very similar to asteroids. Both are remnants of the very distant past, like flying fossils from the origin of the solar system. However, while asteroids consist of metals and rocky material, comets are made up of ice, dust, rocky materials, and organic compounds.
A comet is an object that shows activity, and asteroids generally don't, although there are rare occasions of asteroids that show activity as well. The comets typically have a very eccentric orbit. So when it comes closer to the sunlight warms the gases and ices in the comet and creates a gas and dust tail.
2 missions targeting comets have helped us to unveil some of their secrets. NASA's Deep Impact mission and ESA's Rosetta mission, one of the most important missions led by the European Space Agency. In 2005, some of our ideas about the formation of comets and their role in delivering the elements of life to Earth changed thanks to NASA's Deep Impact mission, which was a pioneer in the study of these mysterious and beautiful celestial bodies. The probe reached the comet Tempel 1 on July 3, 2005, and the following day it successfully released an impactor on the surface of the comet, which generated a brilliant flash of light, later discovered to be ice and dust debris ejecting from the fresh impact crater. The Deep Impact mission was the first attempt to peer beneath the surface of a comet. It revealed a number of new findings about comets and their composition, including evidence of water ice and organic materials.
The Deep Impact mission was a wonderful example of the kinds of technology that we want to have available to us in the future for deflecting the trajectory of a potentially hazardous object. Deep Impact was purposely targeted to impact the nucleus of Comet Tempel 1, not for the purpose of pushing it off course, but for the purpose of studying what the subsurface properties of that comet are like. The side benefit, of course, was this is the first time we'd ever done something like this, purposely targeting a spacecraft to slam into a small object in the near-Earth environment. And so it was a great accidental practice, if you will. It was an unintentional practice of the kinetic impact method of deflecting asteroids.
However, we had to wait almost a decade until the next mission to a comet to discover more about these mysterious celestial bodies. It was ESA's Rosetta mission, a spacecraft sent to the 67P Churyumov-Gerasimenko comet by the European Space Agency, that gave us new evidences about comets. On November 12, 2014, an unbelievable milestone was reached when it successfully deployed its Philae probe on the comet's surface. The first time in history that such an extraordinary feat was achieved. Rosetta gathered significant data on the comet. It revealed that it had a remarkable array of surface features and many processes which contributed to its activity, painting a complex picture of its evolution.
Coming in with the Rosetta mission, one of the strong motivation was whether or not comets played a role in delivering water to the Earth or potentially even organic compounds. I believe some of the outcomes from the Rosetta mission are now clearly showing that the comet didn't really play much of a role in delivering water to the Earth. We can look at isotopes of hydrogen, for instance, and deuterium on the comet, and they have distinct properties to what we find on water on Earth. And so there doesn't seem to be much room for delivery of water from comets. So that is an important aspect. Regarding the organic material, this is still an ongoing debate. Clearly, comets contain lots of organics, and so in principle, there is an opportunity to deliver organic material to the surface of the Earth, but it's totally unclear whether or not they actually played any significant role in the, let's say, formation of complex organics on Earth that eventually led to the formation of life.
The main shocking conclusion after all the data gathered was analyzed was that comets didn't bring water to Earth. Regarding asteroids, there are theories that suggest that they might have planted the ingredients for life on Earth. The key point would be to know how much water they have, which would be considered evidence of how they helped plant the seeds of life on Earth. There are two ongoing missions that may provide an answer to this question: the Japanese Hayabusa 2 mission to the asteroid Ryugu, and NASA's OSIRIS-REx mission to the asteroid Bennu. Both missions will collect asteroidal materials and bring them back to Earth for in-depth analysis.
The OSIRIS-REx mission to asteroid Bennu is a sample return mission to detect amino acids on an asteroid and bring back a pristine sample to Earth for study here.
We will learn a lot from comparing the two asteroids, Bennu and Ryugu, and understand the similarities and differences between their samples. The first one to be launched was JAXA's Hayabusa 2 mission, a mission of the Japanese Aerospace Exploration Agency that left Earth in December 2014.
A Hayabusa 2 mission is visiting an asteroid called Ryugu. It's about 1 kilometer across. It also seems to be a primitive carbonaceous chondrite, but the interesting question is, did it come from a different parent than, let's say, Bennu? It's possible that both of these asteroids came from very different parent bodies originally in the asteroid belt, but it's also possible they came from the same parent body. In the process, we're going to learn about the nature of very large asteroids that are primitive in the asteroid belt.
It successfully reached Ryugu on June 27, 2018. It landed 3 hopping rovers on the surface of the asteroid. Some of these rovers have already sent home stunning images. However, the climax of the mission came on February 22, 2019. That day, the spacecraft was able to make the most complicated maneuver: the first touchdown. The probe was able to grab a tiny sample of dirt off the surface of the asteroid. It was the second time that humanity has ever achieved such a feat. These are the actual images of the historic moment of the first touchdown. Hayabusa 2 is hoping to bring back to Earth between 10 to 100 milligrams of material for in-depth analysis. The goal is to clarify the origin of life by analyzing samples acquired from a primordial celestial body, such as the C-type asteroid, to study organic matter and water in the solar system, and how they coexist while affecting each other. The other asteroid sampling mission that is now underway is NASA's OSIRIS-REx mission. On December 3, 2018, after a 1.2 billion mile journey, it reached its asteroid target, Bennu, and started to orbit. It is scheduled to bring back a sample of this mysterious celestial body to Earth in a sample return capsule in 2023.
The OSIRIS-REx mission launched in September of 2016, and it's a 7-year mission to go out to the asteroid. So we're going to reach the asteroid in 2018 and perform science studies of it through 2019 and 2020. And then in 2021, we will begin our return back to Earth.
The OSIRIS-REx mission will answer some key questions about the origin of the solar system, since, as an asteroid, Bennu is a flying fossil from our solar system's most remote past, and about the origin of life on Earth, since, as a carbonaceous asteroid, it may contain molecular precursors to the origin of life and Earth's oceans.
One of the reasons why we want to find out whether or not there are amino acids on Bennu is because we're not exactly certain how the building blocks of life got on Earth in the first place. One of the theories is that asteroids may have impacted Earth while it was in its early formations, and if those asteroids had amino acids on it, then it would have seeded life here on Earth.
OSIRIS-REx will determine Bennu's physical and chemical properties, which will be critical information to have in the event of an impact mitigation mission. It is scheduled to touch down on the asteroid's surface with the touch-and-go sample acquisition mechanism, or TAGSAM, that consists of a robotic arm with an attached sampler head.
We use the TAGSAM arm, which is kind of like a really expensive vacuum cleaner, which reaches out and touches the surface of Bennu from about 6 feet away and uses nitrogen to stir up the dust and the regolith that's on the surface of the asteroid. And that gets collected inside of a round collection plate, which we then store on side of the spacecraft and bring back to Earth.
From the most distant asteroids orbiting beyond Jupiter to near-Earth objects, each space rock contains clues to trace the epic events that shaped our solar system as we know it today. By studying these small bodies, we can learn more about how they accreted to form larger planets and about the time period when they massively impacted primitive Earth's surface. Everything started with a primordial disk comprised of grains of dust, which were tiny particles of rock, metal, and ice swirling around our primitive sun. Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects.
Well, an asteroid is sort of a leftover piece of the original building blocks which made the planets. Okay, originally we think our solar system was mainly made up of gas and dust. And slowly the dust began to form in larger and larger objects and became objects very similar to the asteroids we have today. Continued to grow, and ultimately they became into planets, they became into large objects in general. But some of the smaller objects that didn't manage to get into the planets became sort of the leftovers, and they're what we know today as asteroids. So these bodies have changed very little since the earliest times in solar system history, about 4.5 billion years ago.
Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects. Two of the most peculiar celestial bodies that may help us understand how the planets were formed are Vesta and Ceres. They are the largest bodies in the main asteroid belt, two protoplanets that never grew enough to become planets. NASA's Dawn spacecraft, which recently ended its mission, orbited both and definitely demonstrated that they are quite different from regular asteroids.
The Dawn mission is a NASA mission that was taught to investigate with great details the main objects in the asteroid belt. The targets were the asteroid Vesta and the dwarf planet Ceres, which are the most massive object in the asteroid belt in between the orbit of Jupiter and Mars. The name of the mission tells already what the mission is about. Dawn means, really try to understand the origin of the solar system, how the solar system was formed. And these objects, the targets of the missions, were considered and are still considered to be objects that formed very early on in the solar systems.
We almost call these dwarf planets. One is called Ceres, which is over 900 kilometers across. The second one is called Vesta, which is over 500 kilometers across. These two asteroids have very different compositions and a very different nature.
On November 1st, 2018, Dawn ended its mission. Currently, it's in orbit around Ceres, where it will remain for decades. Dawn found that while many asteroids are loose collections of rubble, the interiors of Vesta and Ceres are layered with the densest materials at their cores.
The asteroid Vesta seems to almost be like a little version of a planet that formed in the inner solar system. We believe it got so hot that it melted at one point, forming a core. It actually has material on the surface that makes it look like it's actually gone through volcanism, where basaltic material has come out and flowed across the surface of the rest. We actually believe we have some kinds of meteorites that actually came from this asteroid Vesta. And so we've been investigating that world to try to see the differences between what we could see from a spacecraft mission and what we can see from the samples that arrived on the Earth.
It's fascinating to think that we have a chance to directly study a piece of Vesta here on Earth. Thanks to some meteorite samples, the team of the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can investigate the main compounds of the surface of the protoplanet.
This one is a howardite, so it's an impact accretion. And these are little bits of rock on the surface of Vesta that were smashed up during other asteroid impacts. And these bits of rocks were thrown about the surface, accreted together. They were fused together by the regolith, and then a later meteorite impact has thrown this piece off Vesta's surface and it's impacted the Earth. This sample here is a diagenite. So this is like a gabbro that we would find on Earth, and this forms at some level within the crust, and it's an igneous rock. So it crystallized from a magma at some point in time. And if we can study the chemical compositions and the proportions of the minerals that exist in,
the results from the analysis of these samples will give us their precise composition.
In the samples we have for this meteorite, you can find pyroxene and anorthite, you can find some apatite, some spinel, some quartz, of course, and those types of minerals. So the brighter the spot, the more iron content there is. So you see these gray areas have some iron content, but the most iron content is in these white spots, pixels here. So there's a good majority of this meteorite that actually has iron, but there's more concentrated spots throughout it.
The Dawn mission also studied Cirrus, the biggest object in the main asteroid belt, revealing that it was an icy ocean world where water and ammonia reacted with silicate rocks.
Cirrus, instead, is an entirely different object. It's a much higher content of volatiles, potentially also including some water. On Cirrus, we find, for instance, minerals that are the results of what we call aqueous alteration. That simply means when you have rock interacting with water, you can form deposits, for instance, like carbonates. These are common things that we find on Earth. Cirrus and Vesta are considered remnants from the early solar system. By studying these objects, we can really try to understand the details of the early formation of the solar system. This object, along with many other asteroids that are found between Mars and Jupiter, didn't have an opportunity to grow to larger sizes, like a full-blown planet like Mars or the Earth. And there are several reasons why this happened. We think the main reason is because Jupiter, which was a massive planet, is not far from this region of the solar system. Jupiter has enough perturbation to those little planetesimals, small planets that were trying to accrete in order to form a much larger object.
Thanks to several pioneering missions to certain asteroids, we have been able to learn more about the origin of our solar system, about the role asteroids played as the building blocks of planets and in delivering the elements of life. Nonetheless, some unsolved mysteries remain. One of these mysteries is what is at the core of large planets. Although we can indirectly study the deep interiors of planets for clues about their origins, it's impossible to drill down into the core of any sizable object in space, including Earth. Nevertheless, a rare object called Psyche may offer the opportunity to explore a planet-like body's core without any digging. The asteroid Psyche, appears to be the exposed iron-nickel core of a protoplanet, a small world that formed early in our solar system's history, but never reached planetary size. Like Vesta and Ceres, Psyche's path to planethood was disrupted. There's an upcoming mission to this unique and strange asteroid that will help tell the story of planet formation by conducting an in-depth study of this metal object. NASA's Psyche mission. The mission is scheduled to launch in 2022 and will reach its target after a 3.5-year journey in 2026. It will help us to understand a previously unexplored building block of planet formation, iron cores.
We've never actually had a chance to visit a world that's made out of iron, which may be a metal world. We think the way you would get metal worlds is possibly they are the cores that have been extracted from a larger, probably asteroid, or maybe even a small mini-planet that was blown apart by some gigantic collision very long ago. So this is our opportunity to see what cores of worlds may be like. But there's also this interesting question about what should geology be like on an iron world?
The history of the solar system is written in cataclysmic events that began in the early stages of the primordial nebula, that became the primordial disk of grains of dust. Giant collisions between bodies were central to its evolution. The position of the planets has shifted due to huge gravitational interactions, and these planet migrations are thought to have played a key role in the solar system's early evolution. The Trojans, as ancient remnants of that remote past that are trapped in the orbit of some planets, could help us understand what happened. In fact, Jupiter's Trojans could give us clues about what happened the last time Jupiter moved, and about what role it played in the organization of the planets of the solar system.
Lucy is going to visit 6 what we call Trojan asteroids, which are these asteroids that lead or follow Jupiter in its orbit. One of the surprising things about the Trojan asteroids is that although they occupy a very small region of space, just this little region near Jupiter's orbit, they're physically very different from one another. Is that they formed at very different locations in the disk, and the gravitational evolution of the planets led to a large number of objects from that outer region being trapped in this little region.
NASA's upcoming Lucy mission, scheduled to launch in October 2021, will explore Trojans for the first time ever.
We're going to be visiting objects in both swarms. The whole idea of this is to understand the diversity of these Trojan asteroids, what makes them different, because that's going to be a key to understanding how our solar system formed. This is named after the discovery of the Lucy fossil. The Lucy mission is named after the hominid fossil, the Australopithecus fossil, Lucy, that was discovered in the 1970s. Just like the Lucy fossil revolutionized our understanding of hominid development, the Lucy mission will revolutionize our understanding of solar system formation and evolution.
Lucy's discoveries will give us new insights into the origins of our Earth and ourselves. Asteroids don't just make it possible for us to learn about the evolution of the solar system or the formation of the planets. They also offer us almost unlimited resources. They contain natural resources such as water, organics, and precious metals. In the near future, these asteroids may fuel the exploration of the solar system by robotic and manned spacecraft. They could become useful pit stops or stepping stones en route to more distant destinations like Mars or beyond. There are no gas stations in space yet, But scientists and engineers are already starting to think about how asteroids could one day serve as refueling stations for spacecraft on the way to faraway space destinations. These small worlds might also help astronauts restock their supplies of water or other materials. Asteroids are not just small celestial objects, but extremely small worlds that can help us understand our own world, Earth, as well as the solar system. They can offer us clues about its origin, its evolution, the formation of the planets, and even about the origin of life. Current technology allows us to dream of a not-so-distant future where asteroids will be pit stops for deep space exploration, as well as sources for mining metals, minerals, and propellant to be used in space and maybe on Earth. This is only the beginning of the adventure. The exploration of asteroids has just begun. In the last few years, several missions to asteroids have shown us that they have many resources that could be useful to us.
The advantages of asteroids are that they have a lot more favorable chemistry. The components that the asteroids are made of are a lot more of the things that we find valuable.
There is one type of asteroid, the C-type, also known as the carbonaceous or chondrite asteroids, that are the most abundant and have not just hydrocarbons, but also a key element for the future space industry: water. Water is an extremely valuable resource for several reasons. It will be necessary for resupplying. Astronauts could use asteroids as stops to refill the water tanks of spacecrafts in long, deep space journeys to destinations like Mars.
By having water on practically everywhere around the solar system, because there's millions of these asteroids floating around, you have the possibility to use water not just for humans. It's good for drinking. Water can be used to obtain oxygen. You can use them to shield you from radiation, to grow plants, whatever you need. But the real importance of water on asteroids is because you can use them as a means of energy, as a propellant.
You can just heat the water to steam and then use that as a rocket, a steam rocket. And that's a way to get around space. But another way is to take the water and split it by electrolysis into hydrogen and oxygen, and then use that in a liquid hydrogen, liquid oxygen rocket. And that's the most powerful chemical rocket we have today.
So in a way, water becomes, as we say, the oil of space. Because once you have that propellant, that will help you to move around the solar system, get you to much further destinations. You will be able to now refuel, so that you don't have to bring that fuel from Earth. And so that allows you to have larger rockets, larger payloads, and truly they become stepping stones, or sometimes they call it pit stops along the way.
Several missions have recently explored or are exploring several C-type asteroids, as the Hayabusa 1 mission from JAXA, the Japanese Aerospace Exploration Agency, or two ongoing missions, NASA's OSIRIS-REx mission and JAXA's Hayabusa 2. All of these missions have the peculiarity of being sample return missions, which means that probes will grab some asteroidal material and will return it to the Earth for its later analysis. These samples will be extremely useful to know much more about the real composition of asteroids and will allow us to study their real potential as resources. There's another type of asteroid, the M-types, or metallic, which are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed in different proportions with stone. Those asteroids might be used as an endless resource of materials and minerals.
They also are important because Some of those asteroids, the metallic types, hold important metals that are used for a variety of things, for construction, like iron and nickel, and also the valuable platinum group metals. So once you have those metals, now you have the material that you need to develop manufacturing things like, for example, tools or spare parts, or even large construction material for satellites.
There are even some asteroids like Psyche, which are made almost entirely of metal that could eventually become very interesting targets for the future asteroid mining industry, as the metals are on the surface and there's no need to dig deep to extract them, as happens here on Earth, greatly simplifying the mining process. The NASA mission to Psyche, planned for 2022, will allow us to know more about this unique metallic world. All the resources we can extract from asteroids might be really useful for industrial purposes in the near future once the space industry revolution has finally kicked off. Things have been changing very fast in the space industry in the last few years, thanks to the rapid growth of private space companies. The real game changers in the space industrial revolution.
I think we are entering a new era when private entities are taking a bigger role in space than they did before. They're creating a kind of more commercial market for new people to work and live in space that we didn't have before. And that's driving what I think is going to be a new era in space exploration that is less directly tied to government programs, but more commercial activity in space.
This new space industry has several main drivers. On the one hand, improvements in launch systems, sensors, and other input and innovations, such as the small-sat architecture, are driving down costs.
The new space concepts, this idea that there's this environment out there, a potential environment for economic investment and economic return that is effectively boundless. We live on a planet with limited resources. Space around us, the solar system around us, represents economic resources, mining, mineral resources that are effectively boundless.
The combination of decreased costs and increased capabilities of smallsats opens up new use cases, industries, and applications for businesses. All of these have led to the democratization of space, as it will be no longer just territory exclusive to huge national public space agencies, but also for any big or small private companies eager to invest in space.
That is what is pushing not just the governments, but the private industry and the rest of the world, not just the space-faring nations, but the rest of the world, as you're seeing now, is interested in entering this new phase of space. It will be not just for exploration, not just for gathering scientific knowledge, but to truly start using space to help us in commercial activities and economic ventures.
The key driver has undoubtedly been the increasing development of fully reusable rockets that will dramatically reduce the costs of launching. The main reason that space has been, up until now, an industry only affordable to huge space national public institutions such as NASA, ESA, Roscosmos, Russia, or JAXA, Japan. Private companies like SpaceX or Blue Origin, led by multi-billionaire entrepreneurs like Elon Musk or Jeff Bezos, are the ones that are investing most heavily in developing techniques to reduce launching costs. The development of more capable and increasingly smaller satellites is another of the drivers of this coming industrial revolution. Private companies like Planet or OneWeb are leading the production, launch, and control of these nanosats, which will radically improve our network communications, broadcasting systems, geolocation systems, or Earth observation. In addition to the aerospace industry, this space industrial revolution will also transform communications, the internet, tourism, the energy industry, manufacturing, and mining.
There's other opportunities in space entertainment and on-orbit manufacturing, things that will also create revenues and activity and create a demand for an on-orbit facility. I expect all of this to happen in the next 5 to 10 years.
The mining industry will focus especially on the moon and on asteroids as the easiest targets for obtaining resources such as minerals, metals, or water. Asteroid mining, which has belonged to the realm of science fiction until now, could become a reality in the near future. We may be witness to a 21st century gold rush.
The real estate plays when we start launching lots of people to space. It's going to be the manufacturing that we can get going on orbit. It's going to be all of the things that we can do, and you're going to need everything you can possibly imagine on Earth. We're going to need that in space. That's going to create an incredible amount of value. That's going to engage a lot of people.
There are 2 places in the world that concentrate most of the companies responsible for this revolution: California in the United States and Luxembourg, a very small country in the heart of Europe. Luxembourg is a very particular case. It could become the Silicon Valley of asteroid mining. This tiny state took a gamble on the space industry and nowadays hosts the SES, Société Européenne des Satellites, the world's leading satellite operator, with a fleet of about 50 satellites. This country is one of the main accelerators of this emerging space industry revolution.
Luxembourg have become very interested in asteroid mining. They're a fascinating little country, and they're a very little country. But in the 1980s, they helped to set up some of the first commercial telecommunication satellites. And now the largest telecommunication satellites in the world are from Luxembourg. So they're bigger in space than they are on the ground.
The goal of the Luxembourg government is to put into place an overall framework for the exploration and commercial use of resources from celestial bodies such as asteroids. An adventurous and unproven enterprise like space mining requires financial backing, legal frameworks, and favorable regulatory structures to allow the work to even take place. Luxembourg has expertise in this area, given its experience in the mid-1980s with the commercial satellite industry.
They're smart enough to know the financial industry, and they're a fairly concentrated economy in a couple of sectors. So they're now aggressively looking for other wins they can make. How can they get ahead of the game? And so they've realized asteroid mining, it's not just about the regulatory environment. I mean, it's easy enough for them to write favorable regulations so that it makes sense. But they also want to invest to move that forward and really cement their position in the asteroid mining industry.
Asteroid mining could become a big industry within the next decade, depending on how we solve the many technical difficulties involved. The first difficulty is to know which asteroids are the most interesting for mining purposes, as there are asteroids spread all over the solar system.
To know which asteroids to go to, we work with collaborators who have been studying meteorites and remote observation of asteroids. And from our observations, we can determine which type of asteroid it is. And the meteorites tell us kind of the range of possibilities of the mineralogy of those asteroids.
The data gathered by NASA, ESA, the European Space Agency, JAXA, the Japanese Aerospace Exploration Agency, and other space agencies in the last few years on near-Earth asteroids, the most easy accessible, will facilitate the selection of the best targets for asteroid mining companies. Another difficulty would be to decide the best way to mine, whether to bring raw asteroidal material to Earth for use or to process it on-site to bring back only processed materials and perhaps produce propellant for the return trip. or even to transport the asteroid to a safe orbit around the Moon, Earth, or to the International Space Station. This could hypothetically allow for most materials to be used and not wasted.
What makes asteroids unique and different from other bodies like moons or planets is that they are so small that their gravity is practically zero. That low gravity is good for a couple of things. That makes it easier to get to them. The energy that you need to get to them is lower than even to get to the Moon or Mars. So they are easily accessible energetically, not necessarily on time. They may be far away, but it's easy to get to them in energy. But one thing about the very low gravity of them is that all the techniques that we have learned on how to mine or extract materials here on Earth are quite different when you get to an asteroid. You no longer have that gravity that can keep an excavator on the ground and the traction that you need to move around. These things will tend to float. So you have to design different techniques how to extract this material.
At the Center for Space Resources of the Colorado School of Mines, one of the most renowned space research centers in the world, different experiments have been developed to test the specific techniques intended for asteroid mining. The scientific team uses a sophisticated vacuum chamber to recreate the extreme conditions in space more accurately.
Here at the Colorado School of Mines, we focus on creating environments in which we can test mining equipment in space, or potential mining equipment in space. We have a large vacuum chamber in which we can create a low pressure environment that's similar to what we have in space. We can place simulants of asteroid surfaces that are dusty and will create a dust cloud as we work with them. We can pull a vacuum on it to bring the pressure down to a low enough that it's simulating space. And we can do other things like chill it to very cold temperatures as you might have in space. So it mimics the conditions in space.
To recreate the conditions of an asteroid surface for asteroid mining tests with greater accuracy, scientists use simulants composed mainly of silicates such as feldspar and quartz. Most of the simulants are similar to materials we would find in carbonaceous chondrite asteroids, which are the most abundant and most closely studied. Their composition is based on a variety of data sets, including laboratory analysis of meteorites, observation of bolides, remote sensing of asteroids, data from asteroid missions, and scientific modeling. Thanks to all of this data, scientists have been able to produce the simulants with great accuracy in mineral content and particle size.
What we have here are asteroid simulants. We're making simulants of asteroids. We get the raw material for these simulants from our collaborators at the University of Central Florida, who are experts in the mineralogy of asteroids. And then we're making asteroid surfaces. We're creating a simulant of the asteroid surface. This is one example that kind of mimics a large boulder on an asteroid. These here are smaller boulders or cobbles. Friable because asteroid surfaces have rubble strewn across them, of varying sizes from boulder size to hand size to little pellets.
When it comes to developing mining techniques for asteroids, drilling and anchoring are two processes that have to be closely studied due to the peculiar properties of these small celestial bodies. In the case of drilling, the microgravity plays an important role, as the almost total lack of gravity creates different conditions for mining on Earth.
One thing to understand about asteroids is that the gravity on asteroids is very low. In a lot of processes we use for mining on Earth, we use the weight of a vehicle to hold it down so you can dig. But you can't do that on an asteroid.
The data gathered in the microgravity research in core drilling will provide conclusions on the efficiency of drilling to collect asteroid material, as well as the dangers presented by having loose debris so close to the drill operator. After collecting data on the exit patterns of the debris in a microgravity environment, an appropriate capturing device can be designed to ensure maximum collection. Developing a device that collects excess debris will also decrease the potential for damage to the drilling device.
What you can do is build systems that grip the asteroid, or harpoon it and create an anchoring point onto the asteroid. That then gives you a way to hold onto the asteroid while you use some other device to scoop up the parts of the asteroid and move it into some processing system, like cut up a metallic asteroid so that you can take in metals and refine it within some microgravity refining system. We can study the methods you might use to anchor to asteroids. Might look a little bit like a drill or a harpoon, or even just kind of gripping devices that hold onto the surface of an asteroid. And we want to study them, or want to determine ways to design the anchoring equipment so that it provides enough grip so that you can then scoop and scrape and cut the surface of an asteroid.
Considering that the surfaces of many asteroids are made of boulders, pebbles, and little grains, anchoring processes could eventually be really difficult. That's why it's useful to do testing to study the best way to penetrate and anchor to that surface.
What we're basically doing is penetration testing. So what we're doing is we're taking this probe and we're pressing it down into the regolith, into this simulated regolith, because it's made from stuff here on Earth to simulate what we would find on the asteroid. And when we press it down in, we measure the forces that occur both in the upward in all different directions, as well as the torques. The reason for doing that is to kind of understand if we were to land on an asteroid and we wanted to press into the soil, say we want to anchor, or we want to extract water, or we want to build a habitat, or we even just want to understand how the surface of the asteroid is going to move or react when a meteor hits it. We use liquid nitrogen to freeze them because the surface of an asteroid could get as cold typically as 35 Kelvin. We've sealed the liquid nitrogen inside this. What it is basically, it's a probe that can move around in 6 different directions. So it has, can move in X, it can move in Y, and it can move up and down in the Z direction. An auger, so it has flutes that run around it. Those flutes allow material to travel up, so it's sort of like your typical drill bit that you would, or like a screw that would go into a piece of wood or anything like that.
This test analyzes the forces involved when drilling or anchoring on a rocky surface, which would be useful for the future asteroid mining techniques. One of these techniques is surface mining. On some types of asteroids, material may be scraped off the surface using a scoop or auger, or for larger pieces, an active grab. There is strong evidence that many asteroids consist of rubble piles, making this approach possible. Another technique is shaft mining. A mine can be dug into the asteroid and the material extracted through the shaft. This requires precise knowledge to engineer accuracy of astrolocation under the surface regolith and a transportation system to carry the desired ore to the processing facility. The magnetic rake is one intended for metal asteroids. Asteroids with a high metal content may be covered in loose grains that can be gathered by means of a magnet. The question now is whether asteroid mining nowadays is really a feasible industry if we think of it as a mining industry that provides resources for the Earth.
The cost of sending a spacecraft to the asteroid belt used to be about the same as if the spacecraft were made of pure platinum. So it didn't seem to make sense to go out and get diluted platinum from something that cost you so much to send out there.
Nowadays, the most viable option is to mine and process the resources in situ. As with our present technology, the cost of sending a spacecraft and returning it fully loaded back to Earth would be extremely high.
What is more attractive is to use the resources from that asteroid to use it in space. That makes it more economically feasible because bringing it from Earth is extremely expensive. Bringing water from Earth, bringing the iron and the nickel from Earth is very expensive. So then it becomes economically feasible to extract the resources from the asteroid.
Maybe in the future, if we are able to radically reduce the cost of space missions, it could become feasible.
In the asteroid belt, there are orders of magnitude more materials out there than we've ever imagined. So what you have is companies that can get very excited about claiming these future sources of mineral wealth that will eventually become starships and space colonies.
That dream of space colonies on asteroids might not be so far in the future. We now know that there are asteroids made almost entirely of metal that could potentially become an almost endless resource for industries on Earth in the future.
The existence of platinum group metals was probably the very first resource that attracted interest from companies to go and extract those metals from asteroids. Because of their high value on Earth, there's plenty of platinum on those asteroids. In fact, it has been said that an asteroid a couple of kilometers in diameter or in size has more platinum than has ever been mined and probably will be mined in the next 50 years on Earth. The problem again is it economically feasible to go after that platinum? Is extracting the platinum from Earth more expensive than on asteroids? Not at this moment. The amount of money that you need to launch a rocket to get there to extract the platinum at this point is not competitive. But again, at some point, it may become so hard to obtain the platinum from Earth that it will make sense to actually go to an asteroid to do that. The other thing to consider is the moment you start bringing those large amounts of platinum to Earth, the price of the platinum will just collapse immediately. All of a sudden you will have all this metal available that it changes completely the price that we put on this. Obviously, if there's more demand for it, if now that we have more and we can use it in many more applications, then it will make it much more attractive to go after them.
This emerging industry is about to kick off. Undoubtedly, the key game changers are asteroid mining companies that are investing mainly in the development of technologies to make this industry economically feasible. Among the asteroid mining companies, there were two that led the race until recently: Deep Space Industries and Planetary Resources. However, due to the low feasibility of the mineral extraction, they are now in a redefining process. In addition to those, there are other asteroid mining companies, each focusing on specific aspects of this industry, such as the production of propellant from water located in the asteroids, the development of robotics, or the search for the right targets. One of them is TransAstra.
TransAstra has a business plan that's focused on extracting rocket propellant from asteroids. You could call that asteroid mining if you want. And then using that rocket propellant to fill refueling stations in space, to refuel NASA spacecraft and private sector spacecraft. For NASA, it would be refueling spacecraft that are taking astronauts on a mission of exploration. For private sector, we can refuel space tugs that deliver satellites to their destination orbits.
TransAstra is a new kind of aerospace company intended to contribute to the development of the concept of the transcontinental railroad of space. Their vision is for humanity to become a spacefaring species homesteading the solar system.
We can build the transportation network. It's kind of like the transcontinental railroad of space that will make it possible for industries to go in space for a profit.
Their ultimate goal is to turn thousands of asteroids into refueling stations for NASA and commercial spacecraft, opening the frontier for NASA human exploration and commercial industries beyond imaging satellites and telecommunications. They aim to lead the work in supplying services for 21st century industries of asteroid mining, space solar power, space tourism, and manufacturing in space.
That is going to create the greatest industrial revolution in the history of mankind. And we're standing right here at the moment in history when it's about to happen.
The company has a clever mining technique called optical mining that benefits from the solar power to mine the water on asteroids, water to be used as propellant.
One of the best energy sources we have in space is the sun, and that's one way we can use that is by building reflectors that concentrate sunlight to extract and process materials in space. An example of this is a technique called optical mining that is invented by Transastra and Joel Sercel. We are collaborating with Transastra to help understand the basic process of concentrated solar interaction with minerals of C-type asteroids.
Transastra has invented a process that we call optical mining. Optical mining is an approach whereby highly concentrated sunlight is focused onto the surface of an asteroid or other volatile containing body. The highly concentrated sunlight heats and thermally fractures, means it breaks up the surface. So you have the surface of the asteroid or other water-containing extraterrestrial body. The highly concentrated light hits the surface, and as it heats the surface, it fractures it due to the heat. What's really exciting is that the little particles of the broken surface then individually heat up very fast, and all you have to do to get the water and other valuable compounds out of the asteroid is heat it up. The water comes out as vapor. That vapor actually cleans the surface and exposes the next layer of surface and for the sunlight beam to fracture, and it's a continuous process.
The optical mining technique has been tested in vacuum chambers at the Center for Space Resources of the Colorado School of Mines. They use hydrated mineral type simulant, similar to the material found on the surface of an asteroid.
I have the chamber itself, and that makes it a vacuum and allows me to put in samples and make them hot or cold, depending on the kind of test that we're doing. Then I have a lamp on top of it, and that allows me to have sunlight focused down, or simulated sunlight focused down onto my sample. And then inside the chamber, I have samples of many different kinds. We will get the light out using just sunlight. So we'll concentrate it down to a spot, and a column of water vapor will rise from the surface. So this will probably be the first technique that people use when they're gathering space resources. So after the ice on top of the regolith turns into steam and is sublimated, and it's going to form a little cloud. We're going to take a tent and put it on top of this cloud. The tent is going to be colder than the ground underneath, and in this situation, whenever something is the coldest, that's where the ice will stick.
Transastra is developing an innovative mission concept called APIS, an acronym for Asteroid Provided In Situ Supplies, that includes an autonomous spaceship that will be launched on spacecrafts to reach asteroids.
So what we're going to do is we're going to build a spacecraft that's about the size of a pickup truck and launch it out to an asteroid that's about the size of a house. And then this spacecraft that's about the size of a pickup truck will have inflatable structures, and it'll have a bag that it uses to inflate and then enclose the asteroid. And then the solar concentrators will pump sunlight in, and then through the optical mining process, we'll excavate the asteroid, extract the water, and freeze the water in ice bags. So this honeybee mission, as we call it, will take about 6 months to get to the asteroid. It'll do mining for about 3 months, and then it'll take 6 months to get home, and it will bring back 100 tons of ice. And that's the first small industrial scale mission to bring back an economically important quantity of rocket propellant that can change the economics of space. And we think that that will launch a gold rush in space to harvest asteroid material and also material from the lunar poles. And that will make it so inexpensive to operate in space that it will become practical to do things like build solar power stations in space where the sunlight is much more accessible, much more consistent, much more cost effective if you can launch into space inexpensively enough.
When it comes to benefiting from asteroid resources, one of the greatest challenges is knowing which are the best targets among the thousands of asteroids floating in space. Aten Engineering is a company focused on that field. Their goals are to develop technical solutions for the detection, discovery, follow-up, and characterization of near-Earth asteroids.
We're still working to find some of these bodies with our telescopic surveys, and it may actually take a next generation of telescopic surveys, or possibly a space-based telescope specifically designed to find these kinds of objects.
Up to date, more than 10,000 near-Earth asteroids have been discovered. It's not an easy task to find and to follow them up. But thanks to the Minor Planet Center data and tools, Aten Engineering has been able to study and track those objects. The biggest challenge is to characterize them in terms of size, rotation periods, and spectral composition. Until now, less than 10% have been well characterized. It's estimated that with present technology, it will take about a century to study the entire known population.
We use telescopes to look at the spectra of asteroids, and in the spectral signature you can see different things that tell you what it might be. So you can determine if it's a metallic asteroid, or a stony asteroid, or a carbonaceous.
They are now focused on developing accessible technology for characterization to keep pace with discovery. They are working on quick visible spectroscopy and fast cadence light curves that could be obtained with a telescope in just a few days, as well as in long arc astrometry to be used for phase curves that should take months. All of these would undoubtedly accelerate the rate of characterization of near-Earth asteroids, which would help to analyze their potential as resources for mining purposes.
I'm really excited about asteroids, the near-Earth asteroids in particular, as targets for future human and robotic exploration.
Other companies like Off-World are focused not on the study of the asteroid's properties, but on the development of robotic devices to mine autonomously. Their ultimate goal is to create a squad of autonomous robots working under human supervision on other planets and asteroids, which will allow human beings to spread beyond Earth.
While these little asteroids offer us a lot of benefits to go to as targets, there are still a lot of challenges involved with going to a little asteroid like that.
The environment out there is extremely harsh. Human settlers will have to cope with long, deep space journeys, lethal cosmic radiation, zero or lower gravity, or artificial atmosphere. Off-World thinks the best way to minimize the risks of establishing a permanent and sustainable settlement on other planets would be to have a local robotic army that would be in charge of the hard work. Building landing pads, excavating underground habitats, extracting water ice and materials, making drinkable water, breathable air and rocket propellant, manufacturing basic structures and solar cells, producing electricity, and eventually replicating themselves. As the asteroid mining industry grows, thousands of mining robots would be needed everywhere. These robots should be small and robust enough to survive launches on rockets, solar electric powered. Extremely adaptable to work in a wide range of environments on asteroids, the Moon, or Mars without a major redesign. Autonomous and fast learning to survive without on-site human supervision. And modular and reconfigurable to maximize the reuse of launched hardware. The robots should also have self-replication capability using local resources and should be able to manufacture the first off-world computer chips, closing then the robotic self-replication loop. All these asteroid mining companies are now leading a race that could push human beings beyond their natural frontiers to colonize these small, mysterious, rocky worlds in the near future. The potential colonization of asteroids is not an easy task at all, as they are very harsh environments for us, without any shielding from cosmic radiation, as they have no atmospheres or magnetospheres, with extremely low gravity and with a very high chance of collision with other celestial objects. The two main reasons that justify moving off Earth to asteroids would be to benefit from their almost unlimited resources, as well as their colonization as a risk mitigation strategy to ensure the long-term survival of our civilization in case of a planetary catastrophe.
We really want to get the asteroids that are closest to Earth's orbit. There's enough material in those near-Earth asteroids to support maybe 100 billion people living in Earth orbit. There's 1 million times more material in the main asteroid belt. So after we've got people to orbit, we're using this material to live and work and build cities, we can expand to a huge civilization circling the sun. That's pretty exciting.
You're looking for stuff that you want, and specifically, if you're going to turn an asteroid into a place for people to live, you want the kinds of things that would support life. Like especially you would want a certain amount of water. You would want components that you could turn into soil for a greenhouse so that you could grow your own food. You would want sufficient metal concentrations that you could make your own building materials from the base metals. You would want enough precious metals that you could export precious metals to sort of feed yourself and have things to trade with other asteroid colonists or with the moon people or the Earth people or whatever.
Throughout our history, opening new frontiers has thrilled generations of explorers and pioneers. Asteroids could be considered the next frontier. The fact that asteroids are small rocks floating in space offers several advantages, but also some disadvantages. Their extremely low gravity, because of their small size, is one of the greatest advantages. This low gravity would make construction of huge structures much easier and would reduce the costs of landing and launching rockets in comparison to the Moon's or Mars's higher gravity wells.
The gravity is so low on these little objects that it's more akin to going and docking with the International Space Station or rendezvousing with something like the Hubble Space Telescope. So you're not going to be walking on these objects, you're going to be floating near them. And it makes, in some aspects, it makes that portion of doing a mission to one of these objects a lot easier.
Another pro would be the large number of possible sites because of their numbers, with over 300,000 asteroids identified to date, as well as their variety in chemical composition, with carbon-rich, metallic, and stony asteroids.
There are metallic elements and water in the surfaces of those little asteroids that are great resources for us out there in space once we have a thriving working economy out there. If you want to make rocket fuel to power your spacecraft that are moving around the inner solar system, it's a lot easier to make that fuel from the material on a little object with very little gravity than to have to haul it off the Earth all the time and lift it out of this deep gravity well. So the asteroids have great benefits for us, exploration and science and resources. I think they're wonderful destinations.
However, to make this future mining industry a reality, we need to solve several challenges such as asteroids' low gravity and zero atmosphere, which make them vulnerable to cosmic radiation and to the impact of small objects.
We've never actually had any experience in human spaceflight of working in a very low gravity environment that's very geologically dirty. Unlike on the moon, where if you stir up dirt, it very rapidly settles again, on a little asteroid, if you stir up the dirt in that environment, it's going to stay around you in orbit around that asteroid for the entire rest of the duration of your mission. It's going to contaminate your spacecraft, it's going to contaminate your suit, it's going to make the visibility environment difficult. So there are challenges like that. Combining the challenges of a zero gravity EVA, a spacewalk, with the dirty environment of something like the moon is something we have no experience with. And that's going to be, I think, one of the biggest challenges in human crews working around these little objects.
In a not-so-distant future, asteroids may become our new industrial target, a place to mine to benefit from their resources, used not just on Earth, but especially in space.
We can build the infrastructure that moves industry in space, not in 20 or 50 or 100 years, but starting in 3 or 4 or 5 years. And we can be harvesting rocket propellant in less than 10 years and building the transcontinental railroad to the solar system.
They might also become pit stops on the long journeys to Mars, and who knows, to our new home as well.
That is where the value of asteroids really lie, as they become gas stations or pit stops or stepping stones in our process to explore further and further into the solar system.
We are about to go one step further in the conquest of space, as the asteroids could soon become our next frontier.
What is the deadliest threat to the human species? Nuclear war? Global warming? No. The ultimate weapon of mass destruction is a lump of rock spinning through space. It appears almost peaceful, serenely floating through the infinite vastness of the cosmos. Yet this 200 million tons of rock contains more energy than the explosive power of every nuclear bomb on Earth. Naked science now gives you a ringside seat to a massive extraterrestrial impact that, if it happens, could trigger human extinction. Traveling at 50 times the speed of sound, this rock smashes through the protective layer of the Earth's atmosphere as if it weren't there. It strikes, releasing an explosive force equivalent to 100 million megatons of TNT. Across the globe, mega tsunamis and earthquakes flatten cities. Within hours, a plume of vaporized rock bursts through the upper atmosphere expanding around the entire planet. It re-enters as trillions of meteorites, heating up the air to the temperature of an oven. Dust settling in the atmosphere blots out the sun, plunging the planet into total darkness. More than 1.5 billion people die by the end of the day. It could be the beginning of the end for humankind. Hope we have your attention. You may think the Earth inhabits a quiet little corner of the solar system. No. In reality, we live in an extremely dangerous neighborhood. Instead of calmly floating through space, our planet is traveling nearly 70,000 miles per hour through the middle of a celestial shooting range. Speeding through space with us are millions upon millions of lumps of rock. They range from a few feet across to boulders the size of Texas. As we hurtle through space, these rocks cross our path continually. And lacking a giant steering wheel, the Earth has no way of avoiding them. Another threat lurks out there. Comets, frozen lumps of ice and dust, sweeping in from the furthest reaches of the solar system at almost unimaginable speeds. So what are the odds? The chances of an asteroid killing millions of us by the end of the century are 1 in 20,000. We are 4 times more likely to be struck by an asteroid than hit by lightning. The moon, pockmarked from constant bombardment, shows the destructive powers contained within these deadly rocks. Yet the Earth has been hit as often as the moon. When it comes to celestial bombardment, the human race has been lucky so far.
One could strike right this minute, right this second, and totally change life on Earth and possibly extinguish our species.
A rock such as this, when it hits, would have devastating explosive power.
50 million tons of rock coming at 60,000 miles an hour, 10 times all of the nuclear weapons on Earth at the height of the Cold War, going off in one spot.
Yet how can a mere rock wipe out something the size of our planet? And what are we doing to avert such a disaster? The answers may lie in some radical experiments. We examine the threats from comets and asteroids and investigate how scientists are battling to ensure that we can save life on Earth. But first, the evidence. We can find proof of previous bombardments from space here in northern Arizona. This is Meteor Crater, nearly a mile across, 550 feet deep, big enough for 20 football games simultaneously, along with 2 million fans. Scientists originally believed that volcanic activity formed this crater. Then, geologists discovered startling evidence that about 50,000 years ago, a rock from outer space blasted this giant hole. Back then, Neanderthals walked the planet. And this Arizona desert was a temperate wooded plain. And then, out of the sky, a rock about 150 feet across smashed into the ground. It struck with an explosive force greater than 20 million tons of TNT. So how could a rock leave such a massive scar on the landscape? As it entered the atmosphere at over 50,000 miles per hour, friction heated up the asteroid and the air below it to 100,000 degrees Fahrenheit, 10 times hotter than the surface of the sun. But the killer punch was the kinetic energy, the energy of motion stored in the rock. When it hit, that energy became an explosive blend of heat, light, and sound. The asteroid vaporized on impact, launching a cubic mile of rock into the sky. The debris rained back down to Earth, crushing everything within a 5-mile radius. It flattened or killed everything within 50 miles. And this was just a small asteroid. For the full story of the crater, we turn to Eric Asfog, a scientist who specializes in impact crater research. Asfog has been studying asteroids for over a decade. He even has one named after him, 7939 Asfog. Scientists have always cared about asteroids, but as recently as 50 years ago, most thought that they were just harmless lumps of rock zipping around in space. But here at Meteor Crater, scientists uncovered the first clues showing how destructive these harmless rocks could be.
It's one of the most significant holes in the ground on Earth. As recently as the 1950s, it certainly wasn't accepted that this was an impact crater. It was a revolutionary concept in modern geology.
These rocks had been struck by an explosive force far more powerful than any volcano. It changed their very structure.
The smoking gun for a meteorite impact hypothesis was a unique phase of mineral, quartz mineral.
Hit a rock with a hammer and it breaks. Hit it with a truly massive force, and this is what happens. The quartz fractures. Here on Earth, only one process can make what's called shocked quartz. A nuclear explosion. Only something this destructive creates the immense pressures needed to alter quartz in this way. Or an even more powerful force. A big rock from outer space. These discoveries at Meteor Crater led astronomers to begin to take a closer look at asteroids. Scientists found so many asteroids, they started to connect the dots. Space rocks must have hit the Earth many times. The pockmarked surface of the Moon, littered with craters, offered strong supporting evidence. Asfog and others believe an asteroid the size of Meteor Crater hits the Earth every 1,500 years. In fact, an asteroid or comet the size of the Meteor Crater rock may have hit as recently as 100 years ago. In 1908, a vast explosion flattened thousands of square miles of Siberian forest. Luckily, this was truly the middle of nowhere. No one died, but had that strike hit a city, it would have killed hundreds of thousands. So it's clear that the Earth has been getting bombarded from space. But why doesn't our planet's surface look as cratered as the Moon? To answer that, we traveled to Manson, Iowa, the site of one of the biggest impacts ever known. Can we protect our planet from the threat of a killer rock from space? We've seen how often the planet has been bombarded and how it took a big hit in Siberia as recently as 1908. Yet the scars aren't easy to find. Could there be impact craters that nature has simply hidden? This is Manson, Iowa. It looks like many other small towns in America. But Manson has a secret. For years, geologists knew that something was odd about the land around here. Abnormalities had been uncovered as far back as 1912. But just as at Meteor Crater, the scientific community believed that ancient volcanic activity was the culprit. Then, in the mid-1980s, two geologists began a series of drillings. What Ray Anderson and Brian Witzke found changed everything.
As the core came out of the ground, right away we knew there was something that was totally unusual about it. You get a big mixture and juxtaposition of rocks that are normally thousands of feet apart. You'll find a fragment of rock from 10,000 feet down mixed with one that was right at the surface. So something happened to mix all of these up. Once we got a chance to look at them under a microscope, there was nothing in all our years of geologic training to prepare us for what we saw.
The most definitive evidence for large-scale impact at Manson is what's called shock quartz grains. Such tremendous shock forces move through the ground related to this giant explosion. These require such high pressures, there's no way that they could happen under any kind of crustal process that we're aware of.
They'd found shocked quartz on a site 75 million years old. That could only mean one thing: an asteroid impact. So what happened here 75 million years ago?
That day when the meteorite hit at Manson was certainly a very bad day for anything that was in the vicinity. This meteorite would have been somewhere in the area of about 1.5 miles in diameter. That would be something on the order of 50 million tons of rock coming at 60,000 miles an hour. That big a rock at that speed would have not noticed the atmosphere, would have hit the Earth, it would have penetrated into the Earth about its own diameter. And that amount of energy was truly tremendous. 10 times all of the nuclear weapons on Earth at the height of the Cold War going off in one spot.
The asteroid completely vaporized, along with millions of tons of rock and earth.
That vapor would have been shot straight up into the stratosphere and distributed worldwide, blanketing the Earth, basically.
The crater the asteroid carved would dwarf the Grand Canyon. And yet today, there's no visible trace of it. How could such a gigantic hole in the ground have vanished into thin air?
The reason that there's nothing to see there today is because Iowa's been glaciated many times, and the last time the glaciers came into Iowa, 12 or 14,000 years ago, they blanketed the Manson impact structure beneath 50 to 150 feet of glacial deposits.
There was a tremendous amount of devastation, and yet the Earth has managed to cover it all up, and you wouldn't know it's there.
Scientists believe the Earth has been bombarded by asteroids as many times as the Moon. The difference is, the Earth has an astonishing ability to heal its own scars. Unlike the Moon, a barren rock with no atmosphere, the Earth is alive, and its wind, rain, and ice cause constant erosion. Today, there are only a few hundred visible craters left, recording the impacts of these asteroids. But exactly where have these extraterrestrial bombs come from? There are more than 1 billion orbiting in loose formation between Mars and Jupiter, from tiny pebbles to some that are hundreds of miles across. They're spinning through space, moving 30 times faster than a fighter jet. They're the remnants of some would-be planet that at the dawn of the solar system never quite made it. Instead, the awesome gravitational pull of the giant planet Jupiter kept the rocks apart. But sometimes these rocks crash into each other and set off on different orbits closer into the Earth. These are called near-Earth asteroids. They're the real threat to us as they cross the Earth's path around the Sun. They make our part of the solar system a more dangerous place to live. How dangerous? The proof occurred 65 million years ago, when the Earth collided with possibly the largest asteroid ever. A lump of rock so massive that the moment it hit the ground, the back end of it was still more than 6 miles up in the air, higher than the world's tallest mountain. This asteroid impact was so powerful, it may have changed the course of life on Earth. Repeated asteroid impacts on the surface of the Earth have left hidden clues to a moment when life here nearly ended, and to an explosion so awesome that it wiped out 75% of all life on the planet. Some of those clues lie in Trinidad, Colorado, with scientist Dan Durda. Durda is one of the key figures in asteroid research. He's been studying these killer rocks for 20 years. He too has an asteroid named in his honor. These rocks harbor convincing evidence of the ultimate dinosaur massacre, with nature as the hitman. In the lower rocks, dinosaur fossils exist in abundance, but above a clear boundary that the scientists call the KT boundary line, the dinosaurs disappear. So what happened to the dinosaurs? The answer lies here, hidden within this thin white layer of rock. This band of rock contains iridium, a metal so rare on Earth that the average rock contains just 1/billionth of a part of it. Yet in this layer, iridium levels are 200 times normal. Where else do you find a lot of iridium? In space, where it's 1,000 times more abundant than on Earth. The white layer also reveals evidence of shocked quartz, just as at Manson and Meteor Crater. Only an asteroid could leave such a mark. Extra iridium and shocked quartz appear within KT layers at many points around the planet. Such a global footprint could only have come from a truly awesome impact. The asteroid struck near what is now the Yucatan Peninsula in Mexico.
The impact that occurred 65 million years ago was truly enormous. It dwarfs anything in scale that we've ever witnessed in human civilization. The asteroid or comet that struck the Earth at that time was about 6 miles across. It plowed into the surface of the Earth at over 40 times the speed of sound. It was so enormous that when it struck the Earth, its leading face, when it contacted the surface of the Earth, its trailing face was still up at 35,000 feet. That's the altitude that jetliners fly. So this was an enormous mountain of rock slamming into the surface of the Earth.
The energy of the impact was more than 6 million times that of the 1980 eruption of Mount St. Helens. The initial blast knocked down everything within several hundred miles. It flattened whole forests. The shock of the impact created massive earthquakes around the globe. Worse was to come. The plume of vaporized rock broke through the upper atmosphere. Some of the material was blasted halfway to the moon before falling back to Earth.
All of this material re-entering the atmosphere behaved like so many trillions of meteors. That material heats the atmosphere, in fact warming the upper atmosphere to temperatures the equivalent of the inside of a household oven turned to broil.
Some contend that in the following months, dust blocked out the sun. Darkness enveloped the planet. Deprived of sunlight, most plant life died. Animals that eat plants starved. The food chain snapped. The impact released a torrent of carbon gas, the equivalent of 3,000 years of modern fossil fuel burning. It was global warming on a fast track.
It's every environmental catastrophe that you can possibly think of all happening together at the same time.
But we mammals should be grateful for this particular catastrophe. The dinosaurs had ruled the Earth for 150 million years. Their extinction allowed mammals to evolve and dominate the planet.
If it weren't for that impact 65 million years ago, we wouldn't be here. It truly was the crucible of human evolution.
But there's a possible twist. Just as an asteroid ended the reign of the dinosaurs, such an impact today could wipe out the human race.
A KT-size impactor hitting today
in Los Angeles, say, would immediately lay waste and blast flat everything from Denver up to Seattle. In fact, the whole North American continent would be wiped out, and I truly doubt that humans anywhere on the planet would survive such an impact.
But just how real is the danger that we may one day go the way of the dinosaurs? One dedicated asteroid hunter understands the risks better than most. David Levy.
The Earth is traveling on a superhighway, and this particular highway that the Earth has no entrance ramps and no exit ramps, but it does have cross streets. And every one of these cross streets is an orbit of an incoming asteroid or comet. Right now, one of them is crossing our interstate, but we're not there. What we have to worry about is, does one of these objects cross our highway when we get to it?
Every night, Levy works out of his converted garage, scanning the skies for what he calls celestial terrorists.
We take a picture with a CCD, then we take a second one, then we take a third one, and then the computer automatically scans it. And as you can see over here, it has found an asteroid. It looks like a star, but it moves across the background of fixed stars. And the telescope and the clear sky have caught that asteroid.
Thanks to Levy, the world was able to see for the first time the awesome power of a celestial body smashing into a planet. In 1993, David Levy co-discovered a comet on a collision course with Jupiter.
We had no idea what to expect. Shoemaker-Levy 9 might only be about a mile across. Jupiter is so large that if you poured 1,000 Earths into it, you'd still have room for 300 more. Nothing's going to happen. We're not going to see anything. Boy, were we ever wrong. The comets collided with Jupiter at a speed so fast that had they been crossing the United States, they would have crossed it in 1 minute. 140,000 miles an hour.
The comet slammed in pieces into the planet, creating a tunnel of fire. A huge plume of gas rose up through the tunnel. Massive quantities of dark material dropped onto the top of Jupiter's atmosphere. The collisions left a string of scars that were still visible a year later. Each scar the size of Earth.
It was a chance for us to see nature's awesome power. It was as if nature was really teaching us something. Here is how I work. Here is how planets form. Here is how life forms from these planets. Everybody just look at Jupiter and get a lesson in your heritage.
Levy and other scientists believe that comets and asteroids are not just forces of destruction. The Earth was bombarded by comets and asteroids 3.8 billion years ago. One theory is that these rocks contained water and carbon-based molecules in sufficient quantities to trigger the beginnings of life.
It's kind of interesting to think of them as the possible source, our possible ancestry in the night sky, and a very dangerous ancestry. The birth of life has got to be a very violent thing if it comes from the collision of a comet with the Earth. And we saw in 1994 the tail end of that early solar system violence, the collision of a comet against a planet. It's still happening. It happened back then every day, but now it's happening on Jupiter every couple of centuries, and we were lucky enough to see it.
When humankind witnessed the collision of Comet Shoemaker-Levy 9, the shock kick-started a program of asteroid and comet searches funded by NASA. The race was now on to find these potential planet smashers. Many scientists believe it's only a matter of time until an asteroid hits the Earth. So what are our leaders doing about it? Right now, the answer is very little. And alarmingly, we've recently had a very close call. A lump of rock that passed so close to the Earth, it was the cosmic equivalent of a bullet grazing our skin. March 2004, an asteroid 100 feet across hurtles through space at 50,000 miles per hour. It's just 48 hours away and heading in our direction. Researchers have spotted it from their high-tech astronomical observatory in the desert of New Mexico, home to America's leading band of asteroid hunters. While most people remain blissfully unaware, scientists calculate the orbit of the newly designated asteroid, 2004 FH. It's circling the Sun every 9 months between Venus and Earth. It's going to be close, closer than any other asteroid ever discovered nearing our planet. 2 days later, 2004 FH skims over our heads, 26,000 miles above the Earth, near where weather satellites orbit the planet. Captured here on film, it flashes over the southern Atlantic Ocean, close enough to be seen through binoculars. 2004 FH would probably have broken up on entry. But if a larger asteroid ever hits, we're in big trouble. This time we were lucky. But there are millions of rocks out there, and one of them could have our name on it. We've already demonstrated the cataclysmic effects of a 6-mile-wide asteroid smashing into the Earth, wiping out the dinosaurs. And if a big rock is out there right now heading in our direction, just who is trying to find it? Amazingly, the only government doing anything of significance right now is the United States. The annual budget for this asteroid hunt is just $4 million. It's been said there are more people working in an average fast food restaurant than there are scientists tracking asteroids. Most scientists who are tracking asteroids work here in the deserts of New Mexico. This is the Linear Survey, the largest asteroid tracking program on the planet. The Linear team discovered our near-miss asteroid 2004 FH, the 100-foot slab of rock that brushed past the Earth. Jennifer Evans of Linear tells the story of that near-miss.
2004 FH came to within 26,000 miles of the Earth. To put that in perspective, that's where the telecommunications satellites are, the TV satellites, the weather satellites that we're all familiar with.
Scientists believe 1,000 asteroids over half a mile across are now in near-Earth orbit. NASA has set a target for Linear and other survey groups of finding 90% of them by 2008. To date, they've found 60%. So far, none of the asteroids located are due to hit us. But alarmingly, we know nothing about the remaining 40% that we haven't located.
This is a plot of the inner solar system, and if you look around at the circles, outside is Jupiter, Mars, Earth, Venus, Mercury, on into the Sun. What you can see here in green is actually the main belt asteroids. There's over 200,000 of them known. In red are all of the near-Earth asteroids. Those are objects that are crossing the path of Earth at some point or another. Gives you a feel for the density, the type of environment that the Earth is cruising through every single day.
In the race to locate all the near-Earth asteroids before one strikes, the Linear program runs 360 days a year. Using 2 telescopes, they record a series of digital images. The computer then removes any objects like stars that do not move. Anything moving is likely to be an asteroid. In the course of one night's viewing, they record 7,000 frames of digital pictures. They can find as many as 100 new asteroids on a given night. The computer program is so sophisticated, it located 3 asteroids obscured by the brightness of this star. But even when the linear team find an asteroid, they don't instantly know if it poses a threat or not.
When we spot an asteroid, it's a two-dimensional image, and so there are an infinite number of locations where that asteroid can be. It could be very close to us, or it could be out beyond the main belt.
The team can only get an accurate position on the rock by observing it from different points over several days. When they can plot the orbit, they can see if it is on a collision course with the Earth. Simply counting all the near-Earth asteroids is not going to prevent an asteroid strike. We have to find ways of dealing with the threat. But before we can work out how to defend ourselves, we have to know our enemy better. The first steps in gathering that knowledge are being taken in Boulder, Colorado. Here, a NASA-sponsored mission is in the final stages of preparation. It's called Mission Deep Impact. The objective, to rendezvous with a comet, Tempel 1, and crash into its frozen center. This is the first mission of its kind. Scientists calculate that over 1 trillion comets travel through the solar system, although their orbits only rarely bring them close to us. But they're fast. A comet could slam into the Earth at nearly 150,000 miles per hour. Mission Deep Impact uses 2 spacecraft: the larger mothership or flyby, and the impactor, which navigates into the path of Comet Tempel 1. The comet will smash into the impactor at 23,000 miles per hour, creating a crater the size of a 7-story building. The flyby will record the impact event. But is there any danger of the impact changing the orbit of the comet, sending it hurtling towards us?
The comet itself is 3¼ miles in diameter. The impactor is about 1.5 yards wide. So it's essentially the same as a mosquito being overrun by the windshield of a truck. There's really no chance that we're going to destroy the comet or even divert its path.
Soon we will know what lies at the heart of a comet. But we still have very few clues about the makeup of the other celestial rocks. The asteroids. Currently, researchers think there are 3 types of asteroids. They could be one solid piece of rock, or they may be 2 rocks joined together, or they could be a series of smaller rocks held loosely together, a so-called rubble pile. So how do we defend against them? The popular myth, fueled by Hollywood blockbuster movies, suggests that we simply blow them apart with a nuclear bomb. To demonstrate how an asteroid might react to nuclear bombardment, planetary scientist Eric Asfog conducts an unusual demonstration. He's showing what would happen if we tried to destroy the 3 very different types of asteroids. The rubble pile, loosely held by gravity. The binary, side by side through space. The monolith, one solid slab of rock.
Well, let's see what happened here. The monolith, which was the largest chunk of rock, all that's left. And if you go to the next weaker asteroid, the contact binary, you've actually got a couple of pieces here that are left. You know, there's not much to say for it anymore, but there's a couple of sizable fragments. And then if you go all the way over to the weakest of them all, most of the original mass of the rubble pile is still here. And if there's a little bit of gravity over the next hours after that collision, this rubble pile might gather up its pieces again and form itself again into the original asteroid. It's not necessarily the strongest asteroid, which is the one that's going to survive impact bombardment.
But how can we know how a real asteroid will react to our attempts to annihilate it? At NASA's Ames Research Facility in California, naked science watches the destruction of a genuine piece of meteorite. It fell to Earth in Northwest Africa. We're using the awesome power of NASA's hypervelocity gas gun. Its bullets hit the target at 13,000 miles an hour. Under the guidance of scientist Dan Durda, researchers placed the meteorite in a vacuum chamber to simulate conditions in space.
If one day we need to go out and deflect an asteroid, push it out of the way, prevent it from hitting us, we'd like to know how real asteroids behave to being, pushed and prodded.
The total destruction test is designed to shatter the meteorite into tiny fragments. They're testing how different meteorite materials react to the impact.
Oh, that was great. Good shot, good shot. And I think it's pretty safe to say that was a super catastrophic fragmentation.
The experiment on this tiny version of an asteroid confirms the results of our rifle demonstration. Once again, the single piece of rock shatters into 1,000 fragments. But how would a real asteroid react? To really know, we'd need to repeat the experiment with a massive lump of space rock. But single asteroids are not the greatest threat. Rubble piles could prove more dangerous. Most asteroids in near-Earth orbit are sent there by collisions within the asteroid belt. Most scientists believe that such collisions would break apart a single asteroid. So, most asteroids approaching Earth are likely to be rubble piles. How do you ward off a threat like that? Asteroid expert Eric Asfaug.
The Earth is a tiny little dot in the ocean of space. It's the smallest target, and this asteroid, if it's destined to collide with Earth, that means it's very lucky. It's threading its path through space, orbit after orbit after orbit after orbit, and it's finally going to hit us, maybe 100 years from now, maybe 200 years from now. All we have to do is make it miss. To make it miss, if you find it early enough, all you have to do is push on it and change its orbit. And if you can do that, it'll just go sailing right past the Earth. It would be a dramatic sight rather than a calamity.
But pushing a giant asteroid away is risky business, and the consequences if we fail are almost too appalling to contemplate. We're talking potential global destruction. And yet we may be able to avoid it. Proposals do exist to move an asteroid the size of a mountain. Naked science is on the trail of a potential Armageddon asteroid. The question, if one starts heading our way, can we save ourselves from it? We've analyzed the warnings from history, asteroid impacts from the distant past, the extinction of the dinosaurs. We've met the small band of asteroid hunters on the lookout for space rocks on a collision course with Earth. So what else can we do to combat asteroids that are going to mess with us? In San Francisco, there's a man with a plan. Former astronaut Rusty Schweickart. Schweickart was lunar module pilot on the Apollo 9 mission in March 1969. This mission was the first test of the lunar module in space. Schweickart also undertook a 47-minute spacewalk.
It may be because I've flown to space and seen the Earth from outside that this is particularly important to me. There's certainly no question, looking down at the Earth, that one gets a sense of a very extremely precious place. I mean, you realize that everything you care about is down there on that planet. And it's a small place, and it is vulnerable in the long run.
The U.S. government has at least allocated an annual budget of $4 million for tracking asteroids that might hit us. But there's hardly a dime being spent on protecting ourselves if we do find one. Rusty Schweickart believes he has a way of creating an effective defense system. He intends to build a spacecraft, an asteroid tugboat, that can fly to an asteroid, dock with it, and then gently push it to change its orbit. It may sound like science fiction, but Schweikart believes it will work. He knows the only way to prove that his vision can become reality is a practical demonstration. If it works, humankind could control its own destiny.
We humans can assume responsibility from this point forward, we believe, for protecting the Earth from this evolutionary, historical shaper of life on Earth. And now that we're on top of the evolutionary heap, we don't want to go the way of the dinosaurs anymore.
Schweikart's defense system is a radical departure from previous ideas on how we deal with dangerous asteroids. He believes that trying to move the asteroid with extreme force would have little or no effect. The asteroid would either absorb the punch or would simply reform. Instead, Schweikart proposes a gentle push over a large surface area. But this mission currently exists only on the drawing board.
Heaven help us if one has our name on it and hits within the next few years. We're looking at something like 15 or 20 years to develop this kind of a capability.
There's another idea for a planetary defense system in Arizona. Jay Malash of the University of Arizona in Tucson has a very simple solution to the problem. He wants to use the power of the sun to divert any incoming asteroid.
I'm going to use this grapefruit to demonstrate the technique of focusing sunlight and getting some material to vaporize. Now think of the grapefruit as an asteroid that might be very slowly rotating, once every 4 hours or so. And we bring our solar collector up and focus down on the asteroid, and in time we should see that the asteroid begins to be singed. And if we're lucky, we'll see a little smoke coming out. Where we've heated the surface up to the point that material is vaporizing. This vaporized material then acts like the exhaust of a rocket. Very slowly and very gently pushes the asteroid out of collision course with the Earth. The idea of using solar energy, free and abundant in space, focusing that on the surface of the asteroid and vaporizing it, causing it to make a little jet, sort of like a solar-powered rocket, where if we could keep the sunlight on it for long enough, the asteroid would simply move away and move out of a collision course with the Earth.
Already, a company in Los Angeles is making solar reflectors. The largest manufactured to date is 42 feet in diameter. Jay Malash believes that his solar reflector would need to be at least half a mile across. That would take at least 3 years to build and would cost tens of millions of dollars. But why spend money on new technologies such as massive solar collectors or asteroid tugboats? Surely a big enough bomb will get rid of anything.
In terms of the nuclear option, people have been watching movies too long. They get the idea that detonating a nuclear weapon causes an asteroid to just evaporate and the parts scatter to the winds, essentially. In fact, that doesn't happen. An asteroid, half a mile or a mile in diameter, is a mountain, and you're trying to move a mountain with a nuclear weapon.
The Soviet Union detonated the biggest nuclear weapon ever, a 60-megaton bomb. You would need a bomb with the equivalent of 1,000 megatons or more to deflect a large asteroid. But no nukes need apply, because there's an even greater drawback with the nuclear option.
Even if you do manage to break it up in small fragments, those fragments are still targeted on the Earth, and they're now radioactive.
The threat of an asteroid impact is real. About a 1 in 20,000 chance of wiping out millions of us. But scientists are working on a protection plan. They have already found over half of the large near-Earth asteroids and hope to locate 90% of them within the next 4 years. Once we know where they are, we can calculate their trajectories and see if they might hit the Earth.
It's one of the very, very interesting natural hazards. It's the only natural hazard where, in principle, we can tell exactly when it's going to happen. Imagine doing that for a volcano, being able to say this volcano is going to erupt to the minute. 184 years, 12 days, 7 hours, 13 minutes, and 12 seconds from now. So we don't have any predicted impactors yet, but once we discover one that is going to be on its way, and we know exactly when it's going to happen. And it's also a unique natural hazard because we can do something about it.
No government is spending serious money on ways of deflecting these Armageddon asteroids. The question is, how many of them could pose a threat?
I can tell you right now, we know of maybe 3,000 asteroids out there and about 1,000 comets. But what about all the objects we have not yet discovered? I can tell you nothing about those. I can tell you nothing about the fact that there could be an object right now that's going to be coming into the sky while we're doing this interview, exploding loudly and scattering us all, because we haven't discovered it.
We haven't found them yet, but we know they are out there. Asteroids on a collision course with Earth. If an asteroid just a few miles across were to strike tomorrow, we could go the way of the dinosaurs. If we have enough time to work the problem, we could avoid the dinosaurs' fate. But the clock is ticking. Somewhere out there, a killer asteroid may be heading our way. The Sun, a raging nuclear ball of superheated gas, so large, more than 1 million Earths could fit inside. And it makes all life on Earth possible. It powers the growth of plants and forests, providing a continuous stream of energy day in, day out. It has fueled our planet for 4.5 billion long years. To mankind, the Sun's energy seems constant. Since the last major ice age 10,000 years ago, moderate temperatures on Earth have helped man to flourish and build technologically advanced societies. But this may not last forever. We are now beginning to understand that our planet's relationship with the Sun is complex and turbulent. On a regular basis, solar storms rage. Gigantic clouds of plasma fly out from the Sun's surface and strike the Earth's outer atmosphere, sometimes disrupting satellites and power grids.
Every minute, there's a battle going on between the Sun's magnetic field and the Earth's magnetic field.
These sun surges emanate from deep within the Sun, rising to the surface to create visible dark patches called sunspots. The activity of the magnetic fields waxes and wanes over an 11-year cycle. Solar maximum sees the greatest number of sunspots, and solar minimum the fewest. But what does this mean for us on Earth, 93 million miles away? Scientists are just beginning to understand that these magnetic fields may be much more influential than was once thought, and could have been responsible for historical climate change events.
From the historical record, changes in solar activity does have a measurable impact on Earth's climate globally.
A race is now on to understand this connection between the Sun and the Earth, so mankind can prepare for all possible outcomes.
We have liftoff.
Space-based observatories provide us with a unique view of solar activity. In 2006, NASA launched twin state-of-the-art satellites to study at close hand solar storms and sunspots, visible signs of deep magnetic activity that affects the whole solar system. The scientists borrow a trick from 1950s B-movies to create a 3D image of the sun. They deployed 2 satellites orbiting in tandem, one in front of the other, so they can build a 3-dimensional image back on Earth. This 3D image will provide crucial new data on massive explosions of electrified plasma called solar storms. Billions of tons of superheated gas fly into space and buffet the Earth's atmosphere, creating the most dramatic northern and southern lights. Michael Kaiser of the Solar Terrestrial Relations Observatory, or STEREO.
We want to monitor these storms so that we can better predict them. These storms are basically electrical storms, and they can affect spacecraft, ground power systems. The GPS can be upset.
Solar storms are caused by lines of magnetic force ripping through the sun's gaseous surface and snapping, spewing out hot gases and a fierce stream of charged particles, the most powerful type of what's called solar wind. Some storms take 2 days to strike the Earth, while very large ejections arrive in only 12 hours. STEREO could give us time to put satellites and electric power grids into safe mode and move astronauts into protected sections of the space station.
The ones we're interested in, the ones coming right at us, are particularly difficult to estimate the speed and velocity.
A simple demo shows how 2 satellites allow scientists to calculate the speed of this solar wind. Michael Kaiser ejects a jet of liquid at a plate of glass. From the front, it's difficult to measure the speed. This is the way older satellites used to view solar storms. But from the side, you can measure 2 points along the projectile and calculate the speed more easily. Studying solar storms not just from the front, but the side as well, doesn't just reveal their speed. It also shows where they come from. The answer turns out to be the area around sunspots. These dark spots on the sun's surface were shrouded in mystery until the 20th century, when scientists realized that they were connected with the way the sun generates heat at its core. Once scientists understood that the sun got its energy from nuclear reactions, the answer became clear. Nuclear fusion within the sun creates the conditions for powerful magnetic effects. The currents of superheated gas generate intense magnetic fields. As the sun's interior churns, vast loops of magnetic force appear, merge, and disappear, creating sunspots. Luckily, there's a way to visualize it right here on Earth, in the comfort of your own kitchen. NASA astronomer Sten Odenwald compares magnetic field lines to spaghetti.
The surface of the sun is very hot gases that are turning over in a boiling motion. What you're seeing in the pot of water is the convecting water coming up to the surface and releasing its heat and then sinking back down into the pot to get reheated.
The rolling strands of spaghetti are like the magnetic field lines churning beneath the sun's surface.
And these fields come to the surface, get concentrated into sunspots and flares and things like that.
The turbulence that causes sunspots doesn't just come from heat, it also comes from the sun's rotation. On solid planets like the Earth, every part of the planet rotates uniformly. But the sun is a ball of gas, and the same rules don't apply. The equator rotates in 25 days, but the poles take 35 days. The magnetic loops get stretched and distorted as it turns, and where they break the surface, sunspots emerge. Sunspots are immense. A spot can be anything from the size of the African continent to 30 times as wide as the whole Earth. It's thought that the bigger the spot, the bigger the magnetic instability that lies beneath, leading to more severe storms and powerful invisible radiation, like X-rays and gamma rays. And what's weird is that they are not dark at all. They just appear dark because of the brightness around them. In fact, a sunspot is 10 times brighter than the full moon. Solar physicist and expert on sunspot prediction, Leif Svalgaard, can demonstrate how the eye is tricked by this illusion of light, using a small light bulb and an overhead projector. A sunspot is very hot, around 8,000 degrees. It's represented by the glowing filament of this light bulb. This appears bright until Svalbard turns on the overhead projector, which represents the sun.
And if you now switch on the rest of the sun at 10,000 degrees, you will see that the sunspot now appears dark. So it's only by this contrast that it looks dark.
Sunspots are in effect a window on the sun's hidden magnetic activity. But they may also be an indicator of another more profound effect that science is only now beginning to understand. Unknown to medieval astronomers, a dramatic decrease in the number of sunspots may have been linked to a period of significant climate change, now known as the Little Ice Age, a harrowing time when numerous crops failed and some lands became uninhabitable. Sunspots are as familiar to astronomers as the planets and our moon. Up until the middle of the 19th century, they were just an astronomical curiosity. But now, some scientists think that sunspots are visible signs of a mysterious mechanism that spawned significant climate change in Earth's past. Their theories are based on the frequent correlation between sunspot numbers, as recorded by astronomers down the centuries, and climate records. Scientists are now discovering that solar variation affects our climate in complex and subtle ways.
The number of sunspots on the surface, the number of solar flares, the amount of ultraviolet light does have a measurable impact on Earth's climate.
The first record of sunspots dates back to 800 BC. Galileo was the first astronomer to study sunspots scientifically, famously drawing the position of the spots in his notebook. Astronomers' records show that between 1645 and 1714, the numbers were so low as to be almost absent. At the same time, Europe and North America was suffering a period of cooling known as the Little Ice Age, which lasted for around 500 years. But during the Little Ice Age, there was a shorter period of brutal cold, lasting for just over 70 years, known as the Maunder Minimum. One winter during the Little Ice Age, it was possible to walk all the way from Manhattan to Staten Island over the ice. And in London, the Thames froze over for months on end. Londoners even held ice fairs out on the river. The fact that part of this period of severe cold was matched by low sunspot numbers has intrigued scientists ever since. A leading expert on how solar radiance influences our climate, Judith Lean.
There's a lot of anecdotal evidence that connects the sun's variability and climate change through indirect indicators of the sun's brightness and also of the surface temperature. And it's a very controversial topic because to understand it properly, we really need long-term records of the brightness changes itself and of the climate change.
Scientists needed more data, and that was a challenge. Galileo's records are the earliest that give us a clear idea of how much activity was going on. But now scientists have records of sunspots going back over thousands of years. They learned the key was not to look at sunspots themselves, but rather at an astronomical phenomenon which at first glance appears unrelated: cosmic rays. Scientists believe that cosmic rays originate from sources all over the universe, such as massive exploding stars. Charged particles fly out at close to the speed of light. Space is full of cosmic rays. They bombard the Earth continually, and we can measure the intensity of this bombardment over time. Cosmic rays collide with molecules in the atmosphere to produce isotopes, such as carbon-14 in tree rings and beryllium-10 in ice deposits. Thousands of years later, scientists can unearth the hidden records of this bombardment by measuring levels of these isotopes.
We can use carbon-14 to trace the sun's activity cycle going back literally thousands of years. And that's really amazing.
Levels of carbon-14 and beryllium-10 are affected by the sun's magnetic field in space. The sun's magnetic field is vast. Normally it extends 8 billion miles into space. But when the sun is more magnetically active, it stretches to 10 billion miles. Because cosmic rays are charged particles, magnetic fields deflect them. The more magnetically active the sun is, the more cosmic rays are deflected, leaving fewer markers in ancient trees and ice cores. Magnetism has long been used to deflect charged particles on Earth, too. Cathode ray tubes in TV sets do so to create a picture. Oxfordshire, England. At the Rutherford Appleton Advanced Physics Laboratory, British professor Mike Lockwood demonstrates how easily magnetic fields deflect cosmic rays. A simple beam of electrons created in a laboratory behaves in the same way as cosmic rays upon hitting the sun's magnetic field. This glass case contains a green beam of electrons that are physically similar to cosmic rays. Lockwood will simulate the sun's magnetic field with 2 metal coils.
When I pass electric current through a coil, I generate a magnetic field. And so if I turn the current up, I increase the magnetic field inside the bulb, and I start to deflect the beam. And the more I turn the current up, the larger the magnetic field and the more the deflection.
Just like the experiment, when the sun is at its solar maximum every 11 years, the sun deflects more cosmic rays away from Earth. So the number of sunspots appears to be directly related to the amount of cosmic ray deflection. This all ties together with events during the Maunder minimum. The carbon-14 data from trees reveals that the cosmic ray flux increased during this period, which suggests the sun's magnetic field became less active and the spots almost vanished from the surface.
We had the Maunder minimum, where there were few sunspots and a higher than normal flux of cosmic rays. And we can find other examples like that, and we can find periods like recent times when the sun's solar activity has been unprecedentedly high and the cosmic rays have been low as a result.
Thanks to cosmic rays, we have a historical database by which to investigate the changes in our climate and weather systems. Man-made global warming is an indisputable fact. But could solar variation contribute to future climate patterns as well? Solar physicist Leif Svalgaard predicts that the solar cycle could plummet after decades of activity.
There is a chance, since we have had a few large cycles, that the next one will be small.
Svalgaard uses the strength of the magnetic field at the sun's poles to predict future sunspot activity. These fields shown are responsible for recycling sunspots. As a spot fades from view, its residual magnetic field is swept toward the poles by a surface current. At the poles, the flow of magnetic energy sinks to near the core and then moves toward the equator. Then, scientists believe, it begins a return journey toward the surface, being rejuvenated with more magnetic energy along the way. Svalgaard thinks that the amount of magnetic flux that accumulates near the solar poles around sunspot minimum is a measure of how many spots the next maximum will have. More flux means more spots. But even his method is far from foolproof.
There's also a chance that there might be another big cycle before the next one after that being smaller.
One thing is very possible, and that is maybe the next sunspot cycle or the one after that might not come. We might have another one of these Maunder minimum conditions. We don't know. We can't predict things that well yet. But that's always there sort of as a possibility in the future. And we'd like to know if that's going to happen or not.
Every 100,000 years or so, the Earth goes through a major ice age due to a change in the shape of its orbit around the Sun. Our orbit isn't a perfect circle and fluctuates over time, putting the Earth either closer or further away from the Sun. At its most elliptical, there is a 23% difference in solar radiation between the 2 most extreme points in the orbit. Right now, it's only 7%, providing us with a temperate climate since the last major ice age. But what about other influences of the sun, apart from these periodic changes in orbit and tilt? Are changes in solar radiance enough to affect our climate and weather patterns? The answer is, it depends how long the changes last. Sunspots change over an 11-year cycle. But that's not enough time for the small differences in energy output to make a difference. Our planet just can't heat and cool that fast. This is because the oceans absorb lots of energy and take decades, even centuries, to reflect the changes.
There's no doubt that if the solar output decreased by enough over on those timescales, then the Earth would cool in response.
The 11-year cycle has little impact, but that's not the end of the sunspot cycle. Other trends are also found in the records. The Maunder minimum may have been a result of a longer cycle, and that could be long enough to make a real difference. Exactly how much difference?
But the problem is, although you can trace the activity of the sun, it's very hard to trace how the climate of the Earth has changed in step with that.
Accurate climate records going back thousands of years will be the only way to understand if the sun periodically has bigger cycles and potentially a larger impact on global climate. And that's what two American scientists think they have discovered deep in the caves of New Mexico. Scientists are beginning to understand how the sun's magnetic fields may have profound effects on Earth and our solar system. In the past, changes in the sun's magnetic fields may have affected climate and weather patterns for decades and even centuries. The frequency of sunspots, the physical sign of magnetic activity in the sun, seems to match dramatic changes in our climate over the last millennia. But how can we know what the weather was like hundreds and thousands of years ago? Prior to the 19th century, accurate human records of drought and rainfall don't exist. Paleoclimatologist Yamani Asmaram and his colleague Victor Polyak of the University of New Mexico have found an ingenious way to accurately calculate the weather from our Earth's past, using stalagmites in ancient caves.
When you look at the climate record over 10,000 years based on stalagmites, the match is surprising and also fairly robust.
The deep caves of New Mexico in the southwest United States have preserved a perfect record of changes in climate. Through them, these scientists have established a climate record for the American Southwest over a 3,000-year period during the late Holocene. This covers the most recent period of Earth's climate history, from when the last ice age receded.
One of the important attributes of stalagmite is that you can obtain absolute ages precisely, and they also contain annual laminations, just like tree rings, and they contain evidence of climate change at a fine scale.
But to retrieve the data, the samples need careful preparation. The stalagmites go through a three-stage process.
This stalagmite grew from 3,000 years ago to present, and it exhibits annual bandings.
First, a drill grinds out some sample powder.
This is more than enough powder to establish an accurate age for that particular layer.
Next, Polyak mixes the sample with chemicals. This separates the sample into uranium and thorium isotopes. Lastly, the elements go into a mass spectrometer. This process measures the amount of uranium that has decayed over time and the amount of thorium isotopes produced. Because they know how long decay or production of these isotopes takes, they can work out exactly how old the sample is. They can also work out from its chemical and mineral composition how dry the climate was during that particular year. Amazingly, the periods of drought shown by these records accurately match sunspot activity as measured by carbon-14 data. Stalagmites provide accurate records going back hundreds of thousands of years. The scientists' unique methods may explain the mysterious disappearance of an ancient Native American civilization 330 miles north of the caverns in Chaco Canyon. The Chacoan people settled here in northwest New Mexico in 850 AD.
The Chaco complex is considered one of the regional centers for ancestral Americans. At its time, this was a center of activity, very complex, comparable to other communities the world over.
Then suddenly, 400 years later, experts believe the climate dried up dramatically. The Native Americans left the canyon for good.
Unfortunately, in spite of their sophistication, they didn't have the adaptive capability to survive such a dramatic climate change.
The stalagmites recorded these changes with incredible accuracy and revealed that around the year 1250, there was indeed a severe drought. But did the sun force the climate to change? Did it simply produce more heat than normal during this dry period? A simple way to measure the sun's output is to look at how much a small area of Earth is heated during the 11-year solar cycle. On a sunny day, every square yard of this planet's surface receives 1,000 joules of energy per second from the sun. This solar energy, or radiance, is partly absorbed and partly reflected back to space. Over the 11-year solar cycle, this varies by a surprisingly tiny amount. A simple way to demonstrate this change in output is with this basic electric heater, which produces an equivalent amount of power as the sun does per square yard. Solar physicist Joanna Haig shows us how little the difference in heat output really is.
So we can see the intensity that's arriving from the sun. Now, how much of that is varying over the 11-year solar cycle? It's only about 0.1%, and we can see what that means by looking at the radiation coming out, or the light coming out of this little torch here.
Incredibly, this small flashlight generates the same amount of extra energy as the sun does at solar maximum compared to solar minimum.
You can see it's a very small amount, and it's very difficult to understand how this very small change in solar radiance could account for any significant impact on climate.
So, if, as Haig contends, 0.1% is too small to cause the climate change we've seen in the past, then what mechanism is driving those changes in climate as confirmed by records? Haig has a theory. It might not be the sun's brightness that causes the change. It might be another aspect of the sun's energy altogether, one we can't see. Perhaps increases in ultraviolet radiation lead to significant changes in weather and climate. Scientists have discovered a possible link between the dark solar spots of the sun and historical periods of dramatic climate change. But the sun's natural heat output varies very little over an 11-year cycle. People often refer to the sun as a solar constant, as expert Barbara Thompson of NASA testifies.
The solar constant is not really a constant. It's fairly steady. So you'll get throughout the solar cycle variations in how much solar output the sun is putting out. It's not a huge change. You actually need some pretty sophisticated instruments just to measure the change.
So why is there a statistical link between solar activity and historical changes in climate and weather? The answer may lie in the fact that the sun doesn't just generate heat. The sun also generates radiation, with wavelengths in the invisible end of the spectrum. One such type is best known to sunbathers as ultraviolet radiation. We don't see UV rays or microwaves or X-rays for that matter. But the sun generates them along with heat and visible light. Scientists discovered that emissions of these invisible waves also fluctuate over the 11-year solar cycle. UV rays can increase up to 100% from solar minimum to solar maximum when the sun's magnetism is at its strongest. Significantly, recent satellite observations of the sun show it emits more UV when there are more sunspots. So sunspots mean increased UV radiation striking the Earth's atmosphere. This image of the sun, taken from NASA's SOHO satellite, shows the UV rays emitted during a solar storm. And this is the amount of UV radiation emitted during a quiet period of solar minimum.
And by the time you get to the X-ray region, it's varying by 100%, so it's doubling from solar max to solar min over the 11-year cycle.
What other effects could increased amounts of UV have on our climate? UV reacts with oxygen, the chemical element in the atmosphere that gives us life and forms ozone. A layer of ozone surrounds the Earth, providing a blanket of protection.
So on my hand here, I've written a secret code, which you can't read, and you can't read it even if I shine the torch on it. There doesn't seem to be anything on there. If, however, I shine the ultraviolet light, you can see the secret code. And what's happening here is that the chemicals that are in that ink that's on my hand are responding specifically to ultraviolet light, in rather the way that ozone in the stratosphere is going to absorb ultraviolet light and not normal radiation.
The ozone layer is located around 12 to 30 miles above the Earth's surface. It protects us from the worst effects of UV, but it also has another important atmospheric role to play as a greenhouse gas.
So it traps heat radiation that comes from below, and it acts like a blanket and is warming the climate.
When electromagnetic radiation peaks at solar max, ozone levels in the stratosphere rise by about 3%, due to the increase in UV rays reacting with the oxygen molecules. The theory is that this increase in the ozone, along with the extra UV, creates a warm layer which traps air in the lower atmosphere.
So if we change the properties of the stratosphere, if we change its temperature or its height, that affects the circulations of the atmosphere below.
The movement of the hot air in the tropics pushes storm tracks toward the northern Atlantic and Pacific Oceans, which would explain why the Little Ice Age was localized to those areas. For now, scientists can't prove that UV has a large enough influence to cause some of the more dramatic swings in our climate.
Variations in solar activity can definitely affect the climate. The problem we have is in understanding how large these variations are.
So UV radiation is a possible cause of localized climate change. But one lone British scientist thinks there's something else about the sun that affects our planet. Atmospheric physicist Dr. Neil Arnold believes that the solar wind itself might alter climate. The solar wind is made up of a stream of charged particles, high-energy electrons and protons, expelled by the sun constantly, and especially strong during periods of high magnetic activity. Arnold believes that the solar wind collides with Earth's upper atmosphere, called the thermosphere, which in turn stirs up the climate miles below, causing global warming effects.
The solar wind interacts with the Earth's upper atmosphere quite freely, creating big changes there.
This idea flies in the face of conventional thinking about solar wind.
Most scientists would conceive no possibility of it being able to make a significant change to the weather and the climate.
To understand the theory, we have to understand how our climate is kept in balance by Earth's rotation and gravity. These create an effect called the Coriolis force. Our planet's atmosphere has a fine equilibrium. Without the Coriolis force, hot air from the equator would rush to the cooler poles, destabilizing our climate. Instead, atmospheric circulation travels from east to west around the globe, kept in balance by the Earth's rotation. We can demonstrate the Coriolis force by showing how a ball reacts to being rolled in a straight line on a children's merry-go-round. This reveals that the ball rolls in a curved trajectory rather than running straight off the surface of the merry-go-round. So the Coriolis force prevents the circulation of atmosphere from heading toward the cooler poles, driving the system east to west. But Arnold believes that when the solar wind emitted from clouds of plasma strikes the thermosphere, it disrupts this carefully balanced Coriolis force. The hot air moves from warm regions toward the cold polar regions and vice versa. The whole atmosphere is disrupted by the hot air now circulating toward the colder poles. According to Arnold, this overall stirring up prevents some heat from being radiated back into space, raising global temperatures. It's a controversial theory, as solar storms can hit the Earth on a daily basis.
People are skeptical that things happening in the upper atmosphere around a few hundred kilometers, where, for example, low Earth orbiting spacecraft are, actually has an impact on the surface.
If solar storms and UV rays aren't the cause of historical climate change, then what other mechanism could be responsible? As we have seen, paleoclimatologists have well-established records of sun activity over centuries by using isotope analysis and radiocarbon dating. When solar activity is high, the sun's magnetic field balloons, deflecting galactic cosmic rays. When the solar activity is low, more cosmic rays buffet the Earth. Could cosmic rays themselves be the missing link between solar activity and global climate change? The sun is the most powerful object in the solar system. Scientists are just beginning to understand its effects on our planet. It appears that historical changes in climate are linked to the strength of the sun's magnetic fields. Records from the last 1,200 years have shown an emerging pattern of solar influence. Around 800 AD, there was a period of unusually warm weather that lasted for around 400 years. Then the climate seesawed back to cooler conditions. By around 1250, the Viking colonies on Greenland had turned from fertile farmlands into barren wastelands. In the 17th century, London saw the Thames freeze over. Up until the 20th century, the cause of the swings of temperatures was a mystery. The sun seems to be a catalyst, but exactly how it has driven past climate change events is still unknown. One possible explanation involves UV rays and solar storms disrupting our weather systems. But there could be a more subtle and surprising cause, one that begins its life outside our solar system, deep in space. The amount of interstellar cosmic rays hitting the Earth is regulated by the strength of the sun's magnetic field at that particular time. Isotope analysis on ice and tree rings gives us an extraordinary record of this. But what if the cosmic rays themselves affect our climate and weather systems more directly? Could these energetic particles emanating from exploding stars be the actual mechanism behind some climate change? The first clue may be linked to an everyday meteorological phenomenon: clouds. Low-level cloud coverage generally exerts a cooling effect on the Earth's surface. As cloud coverage increases, heat from the sun is reflected back into space. This allows the Earth's surface and oceans to cool down. It's thought by some that a 2% increase in low cloud cover would reduce temperatures back to pre-industrial times. The link between cloud coverage and climate change intrigues Danish physicist Henrik Svensmark.
2% doesn't sound like very much, but it's actually quite important for climate.
Clouds form when rising air from the heated surface of the Earth cools to a point where some of the water vapor molecules clump together faster than they can be pulled apart by their own energy. The water vapor then condenses to form cloud droplets.
With this simple device here, where I have a bottle with a little bit of water in, I can try to demonstrate how clouds form.
First, the water saturates the air inside the bottle. The conditions are now right for forming a cloud. All that's needed is the addition of some tiny particles to act as seeds for the water molecules to clump around. Svensmark will use smoke.
And then I try to do a super saturation by just pressuring this, and then I release, and you'll see that it starts getting wide when I release. And that's because there's a super saturation of vapor and it sticks to these small particles.
The experiment shows that the introduction of a few small particles in the atmosphere could encourage clouds to form. Seeding of clouds happens naturally in our atmosphere. But what if the seeding was supplemented from outside our atmosphere? Svensmark believes that an old theory that cosmic rays can seed clouds might explain climactic periods like the Maunder minimum, a time when the volume of the cosmic rays hitting the Earth was very high.
So you will actually have more clouds on the Earth, and that will give you a cooling of the temperatures.
For the cosmic rays theory to be credible, the team first had to look for a statistical link between cloud coverage and a variation in cosmic rays flux. They analyzed weather satellite records from 1979 to 1992. This period was long enough for the Sun to have completed the well-established 11-year cycle of activity. Svensmark claims to have found that the Earth was 3% cloudier at solar minimum, a statement some scientists dispute. Cosmic rays are invisible to us, but they can be seen indirectly in this special laboratory chamber.
Inside, we have a very high supersaturation of, it's actually alcohol. And when a charged particle goes through, like a cosmic ray, it creates like a contrail of small droplets in its wake. They are everywhere. Maybe 140 particles hits me every second and going straight through my body.
Like any theory, Svensmark needed evidence to back it up. He needed to prove how a cosmic ray could act as a seed in saturated air in the laboratory. In 2005, his team of Danish scientists designed an experiment to see if cosmic rays could seed clouds. The larger chamber was built for testing at sea level, while a smaller one is designed to be taken underground to screen out the rays. The idea is that scientists inject air and trace gases like sulfur dioxide into the tank to imitate the air above the ocean. Instead of the sun, they use a UV lamp attached to one end. The last element doesn't need any assistance. Cosmic rays penetrate the steel outer casing naturally. As cosmic rays naturally strip electrons from the artificial air, clumps of molecules form around these tiny charged particles. These cloud condensation nuclei are recorded by a special counter. The Danes have shown perhaps the very first stage of the formation of cloud condensation nuclei. But they need evidence that the particles could grow bigger before forming water droplets. And that requires more research in more controlled conditions. Such research is planned for 2010 and will take place at CERN in Switzerland, in the world's largest particle accelerator, sunk deep underground. A beam of accelerated particles simulating cosmic rays will be fired into saturated air. Only then could we discover if the Danes' small particles really can grow to the size where clouds begin to form.
This will be a very interesting experiment because this whole area is something we know very little about, that it could confirm the theory that they could grow into something big enough to help clouds form.
Scientists are only just discovering the extent to which our sun influences Earth's climate and weather patterns. 30 years ago, few thought that solar variation had any influence on climate variation, but a small growing band of scientists believe that it certainly does. If the solar cycles are really helping to drive our climate, then the activity of the sun will be crucial to the Earth over the next century.
We're beginning to understand there are these subtle links between the solar wind and aspects of our atmosphere.
Man-made greenhouse gases are warming our planet, but could big changes in the sun's magnetic activity also be an important factor in the future? If there is a crash, then global warming may be slower than expected, potentially saving parts of the globe from flood and famine. Despite this possibility, many believe that carbon emissions would still need to be cut.
We need to still continue with that, because when the sun finishes going through its 100-year period of low activity, we're going to be right back to where we started before with a vengeance.
We know we have the power to change our planet's climate. It's a power we need to use responsibly, but ours is not the only power at work.
Variations in the sun have happened over eons, and changes in the energy coming out of the sun will affect climate on Earth, because the energy is the main driving force for climate.
The sun has been influencing the long-term climate here on Earth for as long as we've measured. It could be that the less magnetically active it is, the cooler we become. We don't fully understand how it happens, be it UV rays, solar wind, or even cosmic rays. But one thing is certain: our well-being and the well-being of planet Earth is dependent on the sun in ways we're only now beginning to understand.